Hello everyone. Today I might be completely intentional. It's not like I would get the entire knowledge of education, but as much as possible. So our target is now it's 458. So we should reach 490 or 490. Let's see. And my voice is really can't speak much longer. And this book is very Harrison Harris. Yeah, David Bowie Harris from South Africa. So global systems of the computer system performance of the elastic process and architecture. Okay, so usually the system that could be accessed in a single process. However, this should be only for a very small number or a very slow processor. Early processors were relatively slow, so memory was able to keep up. But processors speed has increased at a faster rate than memory speeds. DRAM memories are currently 10 to 100 times slower than processors. Increasing RAM between processor and DRAM speeds demands increasingly ingenious memory systems to write across the memory bubbles as fast as speed processing. The sharper is used practically instantly compressed chaos almost as cost to kill. So usually like back in maybe 30 years back, those DRAM memories and now also there is very little improvement in those DRAM memories. We are good at the performance, but not as much as the performance of the CPU is getting right. So the CPU is currently working on gigs of clock frequency, but the RAM is 100 times less than that. So it's an issue. This is the communication systems that are memory or in deficit. Okay, this is the interface. Okay, this is writing address for selecting particular location. This is where writing the data onto the memory, and this is where reading the memory from reading the data from memory. The processor communicates with the memory system via memory interface and shows the memory interface with the interface units. Processor sends to the address, memory intensity data, memory write is one, and processor sends data to memory. Okay, so the major issues in memory system is some tiny projects is the metaphor of books in a library. Okay, so we are discussing about the issues in the memory systems, why memory system has to be updated, like or even introduce a new sorry, okay, a books in library. A library contains many books on the shelves. If you are writing about only meaning of trees, okay, you might go to the library and study the interpretation and interpretation of dreams of the shelf and bring it to the opportunity. You might put it back and pull out journals, the psychology of unconscious. You might so we're just bringing books from the shelf and returning it back to the shelf and again bringing another book back and forth to the cubicle under the shelf. Right? So pretty soon you would get tired of walking from your book to the stacks. If you are clever, you would have like you would save time like to fill the books in the cubicle rather than jumping them back and forth. Okay? Rather than going every time for a new book and reading it back. You might not like it or you might not get the misinformation what you deserve of. If you go back and put it back, you pull out another new book. So he's saying that if we are clever enough, as we know what we are searching for, we are right isn't term but what is that? Traits. So we are writing some around traits. So we know what kind of books to search for. So first go to the shelves and select all necessary books that are related to trains and put them on the cubicle. So in that way we are not doing every time for the book, right? So I just complete all the books that I have brought in one go and then later if I really need some other books then I just take these bunch of books and put it back in the shelf and got some other chunk of books. So this is a effective way. Okay? This method emphasizes the principle introduced in this topic one of making the common case fast. Okay, common cases like writing around trees. So common cases trees. In a library, there will be numerous kind of books. Right? So we are just categorizing it. We are just selecting some specific books that are related to dreams. So there will be some common traits of dreams in this whole library books. By keeping books that you have recently used, okay, or might like to use in the future, like your thinking, okay, you reduce number of time consuming trips to the stacks. Okay, I'll be reducing time like from processor to the main memory. If the address has to go from processor to the main memory and pull out the data from the stack of memory on onto the read bus, and the read bus has to carry the data to the CPU. So this takes some time, right? So this is the time that it takes to have this entire thing. So here we are reducing this time. So okay, in particular, you use the principles of temporal and spatial locality. Okay, spatial locality. Let's first spatial is something related to physical area, right? Space. something like this, relating to worldly as a point to speak. Okay, time. Okay, makes sense. See, in particular, you use the principles of temporal and spatial locality. Okay, what we are doing is, in past, I have, I might have used some books, and those might be helpful, and I just keep them aside near my cubicle itself. And while even going for a single book, I would gather a multiple books along this single book because uh, let's say in library how the books are arranged, it will be like uh, one shelf would contain one kind of one category of books and other shelf would contain other category of books. So I went to dreams category and there are some numerous number of books in stacked together. So instead of bringing a single book, I would rather bring all the not all the books, at least as much as I require. I'll bring those books. So this is something spatial locality. And after using specific books near my cubicle, that is processor core, I would not just return them back to library shelf. I would just keep them aside for some time. They might be, they might come handy in future. So this is temporal. I think basically temporal locality means that if you have used a book recently, yes, you are likely to use it again soon. Okay, since I have used something, then that is really important for me, or it is necessary for me, right? So there might be chance that I would use it again. So I'll just store it. I'll just keep it in my near my cubicle. So spatial locality means that when you use one particular book, you are likely to be interested in other books on the same shelf. So as we have discussed earlier, the library itself makes the common case fast by wait, library itself makes the common case fast. Okay, by using these principles of locality. Okay, yeah, okay. The library has neither the shelf space or nor the budget to accommodate all the books in the world. Instead, it puts some of the lesser used books. Okay, in deep storage in the basement. Also, it may have an interlibrary loan agreement with nearby libraries so that it can offer more books than it physically carries. Okay, library itself, uh, common case, common case, right? Like, library itself makes the common case because in library we have shelves and each shelf is categorized into some sections, right? In dream section, I would bring let's say 10 books related to dreams. Then that makes my life easy, right? I wouldn't go to shelves every time, and I would rather bring them and get one go. So this reduces my time consumption to travel from cubicle to cubicle. And again, he is mentioning that library won't contain all the books. That's true. The uniqueness could not accommodate um, every book in this world. So we might be having some books in the basements, uh, which are not frequently used by the users. So most frequently used books are put in shelves, which are easily accessible and which are not frequently used are kept stored in the basement. Or even we can say that we can borrow from other libraries. If we have some agreements with the other library, we can bring those. So I could relate the library as a cache memory, and this basement or the other library which is linked to this current library as the main memory, I could say that. Or even we have levels. So we'll see. Makes common keys, fast forward. Library has crucial space, not a budget to accommodate all the books in the world. Okay. In summary, you obtain the benefits of both a large collection and quick access to most common used books through a hierarchy of stores. Okay. Cubicle is something that I have, sorry, cubicle is something that is my nearest place where I could stack a bunch of books. And shelf is somewhat far from me, and it has some more than 100 books, I would say. And in basement, I would have thousands of books. Okay, this is the memory hierarchy. Mm, Hierarchy of storage. The most commonly used books are in your cubicle. Okay. A larger collection is on the shelves, and an even larger collection is available with advanced notice from the basement and other libraries. Okay, if we intimate them in advance, they will bring those books from the basement or other uh, libraries. Similarly, memory memory systems use a hierarchy of storage to quickly access the most commonly used data while still having the capacity to store larger amounts of data. Okay. Memory subsystems suitable its hierarchy were introduced in section 5.5. Computer memories are primarily built from DRAMs and SRAMs. Okay, ideally, computer memory systems is first large and cheap. In practice, a single memory only has two of these three attributes. Okay, it is either slow, small, expensive. So let's say it's expensive and small. Then that is what I would say SRAM. SRAM is uh, SRAM density is less, but it is expensive. And if slow and small is considered, then I would say DRAM is slow and the density is very high since the cell is small, like each cell, memory cell is small. Slow and expensive. Mm, okay. Slow and expensive, expensive but slow. But I would say need that slow and need that. But computer systems can approximate the ideal by combining a fast small chip, sorry, fast small cheap memory and a low and a slow large cheap. Okay, need speed. Then we just degrade this attribute of having the capacity as small and we will make it cheap. If it is large, it will be expensive. So we will make it small. So and a slow, large, cheap memory. So if it is large, it will become expensive. So in order to make this cheap, we make this attribute slow. We wouldn't use any faster uh, memory designs. We use slower designs, like let's say DRAM. So the fast memory stores the most commonly used data and instructions. Makes sense. If we are commonly using some instructions and data, then would be it would be a great idea to store that in a faster memory access via storage. So on average, the memory system appears fast. Okay, the large memory stores the remainder of the data and instructions, so the overall capacity is large. Mhm. So, so on an average, memory system appears fast. The large memory stores the remainder of the data and instructions. Okay, most frequently used instructions and data are stored in faster uh, at smaller storage element, right? So those will be stored in that storage, and the remaining instructions and data are stored in large memory, which is slower. The combination of two cheap memories is much less expensive than a single faster large memory. Okay, these principles extend to using an entire hierarchy of memories of increasing capacity and decreasing speed. These principles extend to using an entire hierarchy of memory, increasing capacity. Okay, so we are considering this hierarchy. So lowest hierarchy we have the lowest size like capacity, but the speed is very high. It is the highest, and as we go higher, capacity increases, speed decreases. As we go further away, capacity increases even more, but the speed has decreased tremendously. So that is the hierarchy. I might be able to draw something out of this highlight this one. Mm, let's create a notebook. I think I don't have any notes regarding memory. Memories, subsystems. So memory is a subsystem for the main processing. Okay, let's rename this as cache. So this is as we go up, capacity increases, and as we come down, let's make it height increases and speed increases as we go down. Mm, okay, let's make this together. Speed decreases. This is another level, another level, another level. So as you can see, capacity tends like capacity increases. Large storage stores, okay, computer memory is temporarily built from DRAM chips in 2006. The typical PC had a main memory consisting of 56 MB to 1 GB of DRAM. DRAM cost about $100 per gigabyte. Okay, 1 GB is like 8,000. DRAM prices have declined at about 50% per year for the last 3 decades, and the memory capacity has grown at the same rate. So the total cost of the memory in a PC has remained roughly constant. Unfortunately, DRAM speed has improved by only 7% per year, whereas processor performance has improved at a rate of 30 to 50% per year, as shown in figure 6.2. Okay, so this is the processor performance. Okay, year by year it has been increasing tremendously, but the memory performance is decreasing. So this works at some clock frequency, but this cannot cope up with that speed. So we need some bridging. That is the hierarchy of memory that we are going to be learning today. DRAM prices are okay. The plot shows memory and processor speeds. The 1980 speeds as the baseline, in about 1980 processor and memory speeds were the same. But performance has diverged since then, with memory is badly lacking. DRAM could keep up with processors in 1990 and early 1990s, but it is now woefully, woefully too slow. Okay, woefully. Okay, this is very slow. DRAM access time is 1 to 2 orders of magnitude longer than the processor cycle time. Okay, tens of nanoseconds compared to less than 1 nanosecond. Mhm. To counteract this trend, computers store the most commonly used instruction and data in a faster but smaller memory called cache. So most commonly used instructions and data in a faster but smaller memory. Mm, The cache is usually built out of the same chip as the processor. Cache speed is comparable to processor speed because because the on-chip memory eliminates lengthy delays. Okay, the like if the CPU had to communicate with the main memory, that is DRAM, it has to travel long distances. Right? It is very lengthy. Or in the same IC, if I have this CPU core and memory that we are talking about is cached, then there is very little to no uh, distance between cache memory and CPU. There is some distance which is negligible when compared to this. On-chip SRAM costs were on the order of $10,000 per GB. So on-chip SRAM memory costs around $10,000 per GB. Let's say if I need 1 KB, how much it would be? It would be $10. Okay, 1 KB on-chip SRAM is $10. Let's say I need how much? Okay. 1 GB costs $10,000. Then 1 KB costs, oh, okay, sorry, sorry. So 1 MB costs $10. Okay, 1 MB of on-chip SRAM is $10. But the cache is relatively small, kilobytes to a few megabytes. So the overall cost is low. Okay, cache caches can store both instruction and data. Okay, it can store instructions and data. But we will refer to the contents generically data. Okay, in general, we consider whatever the information that is stored in cache as data. If the processor requests data that is available in the cache, okay, it is returned quickly. Okay, it is called cache hit. Okay, makes sense because if there is no uh, desired information in the cache, then how could it return it? So if there is a desired data, aggressive data, then it is a hit, cache hit. Like we have the address that we desire of. Otherwise, the processor retrieves the data from the mainland. Okay. If the data is not there, it will be retrieved from mainland. This is called cache miss. Okay. We try to get the data from cache and it was a miss. We had to go to mainland. So it's a cache missing data from missing data in cache memory. That's why we have gone to main memory. The cache hits most of the time when the processor seldom has to wait for the slow main memory. The cache hits most of the time when the processor seldom has slow main memory and average access time is low. Guys, I don't know Not often, rarely. Okay. So if the cache hits most of the time in the sense, let's say I have tried to access some data, some addresses. For around, I tried for 100 addresses, and most of the time it had been a hit. So then the is rarely like processor rarely has to wait for the main memory to give the data. So we are not frequently accessing the main memory. If the cache hits are more, so in a way, average access time is low. The third level in the memory hierarchy is the hard disk. Okay, so we have CPU and we have cache and we have main memory and then we have disk hard disk. So this is the memory hierarchy. Uh, okay, third level is the hard disk or hard drive. Okay, hard drive. The same way what the library uses the same uses the basement to store the projects that do not fit in the stacks. Okay, computer systems use the hard disk to store data that doesn't fit in main memory. In 2006, the hard disk cost less than $1 a GB and had an access time of about 10 milliseconds. Hard disk costs have decreased 60% per year, but access times is improved. Like there is no improvement at all. The hard disk provides an illusion of more capacity than actually exists in the main memory. Okay, it is first called virtual memory. Oh wait, um, just a second. Okay. Mhm. Mhm. So what is this virtual memory? So the hard disk provides an illusion of memory capacity. Hard disk provides an illusion of more capacity than actually exists in the main memory. So actually main memory is around let's say 4 GB or 8 GB or even 16 GB, 32 GB, something like that. But hard disk is around 256 GB or 512 or 1 TB, really, really large, right? More than 4 times, 10 times larger than the RAM. So, so it's creating an illusion of more capacity than actually existing main memory. So we think memory, like main memory, is the mm, is the highest. No, okay. For a CPU, for a processor, main memory is everything. Like if I want something, then I could only access from main memory. So this is the interpretation of processor. So it thinks that whatever that I want will be in main memory. And somehow we have designed some hierarchy of cache such that most frequently used data is stored in cache. And if it had been a miss, if there is no data in the cache that we desire of, then we go for main memory. Main memory is the like, last point for the process. So that's not the case. Main memory is also connected to hard disk. So this hard disk kind of imagine like uh, it kind of creates an illusion that it acts like a virtual memory for main memory. Okay, it's not that it's uh, its physical appearance is not there uh, on the motherboard. It's there, but main memory acts as a virtual memory. So it's like books in the basement. Okay, uh, okay, like books in the basement. Data in virtual memory. Okay, data in virtual memory takes a long time to access. Main memory, also called physical memory, holds a subset of virtual memory. Okay, hence the main memory can be viewed as a cache for the most commonly used data from the hard disk. Okay, so we have hard disk, right? So that hard disk, this hard disk, let's say the main memory, let's say. And now this main memory, what we so-called main memory, acts as a cache now. Cache is just a terminology, okay? Um, let's say hard disk में जो भी data है, whatever the data that is there in hard disk will be stored in that. And this main memory will be having the most frequently used data on the hard disk. Okay, and cache contains the most frequently used data in the main memory. So, what is this most frequently used? Who is using this? CPU is using this, right? Using the data. So, CPU CPU's most frequently used data will be stored in cache, and this cache gets the data from main memory. Main memory stores the frequently used data in the hard disk. So hard disk is the final one, and we can use some inputs as well, some inputs to keep the data, like pen drives or some SD cards, something like that. So we need to highlight some words that are really important. One is virtual memory, and why is it not highlighted? Okay. One is virtual memory, and okay, hard disk, right? Okay, hard disk is called as virtual memory. It is similar to hexadecimal. Okay, clear. And main memory is something. So these terminologies are based on the access times. So how fast the CPU can access a memory location in this hierarchy. If it is really long, we do not consider it as a proper memory storage for CPU's performance. So it is there, storage element is there, but we do not consider it. It acts like a virtual memory. So hard disk is a virtual memory, and we bring in the most frequently used data from the hard disk to the main memory. So main memory is the physical memory, holds a subset of virtual memory. Hence, the memory can be used as flash. Okay, summarizes the memory hierarchy. Okay, point 3. A typical memory hierarchy. So there is a processor, CPU, cache memory. So cache memory actually runs at the clock frequency of CPU. So we have given the same clock. So this entire chip IC connects to main memory. So yeah, so this is the physical memory we would say, and this contains the most frequently used data on the hard disk. So hard disk is a virtual memory. It's a virtual thing. We will bring the actually some set of data in hard disk onto the main memory. Summarizes the memory hierarchy of the computer system. Okay, whatever we're gonna be studying from now on has been simply illustrated in this block diagram memory hierarchy. So the processor first looks data in small but fast cache that is usually located in the same chip. Okay. If the data isn't available in cache, the processor then looks in main memory. If the data is in there, the processor fetches the data from virtual memory on the large but slow hard disk. Figure 8.4 illustrates this capacity and speed trade-off in the memory hierarchy, and this typically cause when access time in 2006 technology as access time decreases, speed increases. Okay. I can actually highlight virtual memory is TBM. Wait, I'm sorry. So main memory is the DRAM and cache. Cache is external. Okay, this and then around gigs of clock frequency. So this is hard disk. Virtual memory. This is physical memory. And cache is on-chip memory. Correct. So section 8.2 introduces memory system performance analysis. So we have discussed everything on a high level, abstract level. So we'll dive into the memory system and we'll just analyze the performance. Performance is analyzed on the basis of access time. If the access time is less, it is more. So that is mentioned as access time decreases, speed increases. Memory system performance analysis. So designers and computer developers okay, need quantitative ways to measure the performance of memory systems to evaluate the cost benefit trade-offs of various alternatives. Memory system performance metrics are bit rate or bit rate and average memory access time. So memory systems contain cache memory. CPU is linked to like connected to cache. Cache is connected to main memory, which is physical memory. And physical memory is connected to virtual memory, which is hard. So this is the memory system, and we need to like analyze the performance. The metrics are disk rate, bit rate, and average memory access time. Disk rate, if the desired data by the processor CPU is a miss, it's not there in cache, then we need to go for main memory. So, so main memory access time is higher. So, wait, what am I trying to say? So, what is this rate? This rate is if you try to access some 100 addresses and there had 70 hits, hit in the sense the 70 addresses are there in the cache. So, this rate is what like in 100 attempts, 70 are hit, 30 are misses, right? So 30 by 100, 30% miss rate, hit rate is 70%. So what is this average access time like? Why wouldn't we just include access time? So we are averaging something. So there are some two kinds of accessing times. If the data is there in cache, if it had been a hit, the access time is 70. And if the data is a miss, we have to go to main memory and fetch, right? So this access time is different. It is actually higher than the previous one. So access times are varying. So we just average the access time. So these are the parameters. Miss and hit rates are calculated as okay. Miss rate number of misses per number of total memory access. So how many times you have access to the memory and how many times there are misses. Okay, miss rate. So it is equal to 1 minus hit rate. So rate is something that is how what do we say? Ratio thing, right? So probability. So hit rate is a probability. Let me mark it with different color. So hit rate is number of hits. So hit rate is number of hits or number of total number of access to the calculating cache performance. Suppose the program has 2000 data access instructions, loads or shows a few, and 150 of these requested data values are found in the cache. Okay. The other 150 data values are supplied to the processor by main memory or hard disk memory. What are the miss and hit rates? So there are 2000 data access instructions. So we are trying to access data 2000 times. Okay. Out of that 150 are hits. We found the data in cache. 750 are miss. We didn't find it in cache. We have to go from the memory or hard disk. So hit rate is 150 by 2000 and miss rate is hit rate is 150 by 2000. Miss rate is 750 by 2000. So miss rate, hit rate, average memory access time. So in that, let me see if Google says the same thing. Okay, okay, fine. Average access time is the average time a processor must wait for memory or load or store instruction. Here, typical computer system figure 8.3, figure 8.3. So this is stable. This is 8.5. This is 8.4. 8.3. Okay. In the typical computer system configure 8.3, the processor first looks for the data in the cache. If the cache misses, the processor then looks in memory. If the main memory misses, the processor accesses virtual memory on the hard disk. Thus, AMAT is calculated as e-cache data accessing time from cache memory, e-cache. And if it had been a miss, there is a miss rate. Actually, so M is the miss rate and R cache. R cache. Wait, what is R cache? You can say that this is main memory, this is virtual memory, and RM. What could that be? Let me write out. So inlet is in cache plus R cache. If it is a hit, so we go for this time. And if it is a miss, we go for this. Let's say main memory is everything. So if it is not there in main memory, so nowhere else we could find this data. So let's so I would say in cash plus mm, misrate. Okay, MR is misrate. Misrate of cache into time it takes to access the main memory. Okay, but we have like this main memory misrate as well. So this time change. So if it is a miss, okay, misrate of main memory multiplied by time to access virtual memory. So now I could write this entire thing as cache, this rate of cache multiplied by this rate of main memory. Actually, let's करना था okay. What if it is a hit? So time to access main memory plus this rate of main memory into time to access virtual memory. So here let me highlight this. Take and highlight this column. Cache is blue. So cache is blue. And powerful virtual and what else? And main memory. So this is the entire thing. The T-cache, TMM, TVM, audio access times of cache, memory, virtual memory, NAR cache, NAR, and the cache memory space respectively. Okay, calculating average memory access time. Suppose a computer system has a memory organization with only two levels of hierarchy, a cache and main memory. So there is no virtual memory thing. What is the average memory access time? Given the access times and mistakes given in table F11, so access times and mistakes, so the mistakes are given. Okay, so average access time access time of cache is 1 plus if it is a miss access time of memory is 100. So it is correct. So 10% is 6 must be 11 subjects. most famous analyzed an observation in mathematical accuracy, improving access time. Okay, an access time and 11:30 average number of access time means that the processor spends 10 cycles waiting for data for every 1 cycle. 11 cycle average number of access time means that the processor. Okay, 11 cycle average memory access time means the processor spends 10 cycles waiting for data for every 1 cycle actually using that data. Okay. Mm, Here we said is 10, so I would be spending 10 cycles um, on an average, right? On an average, I would be spending 10 cycles for waiting for data to come from my memory. Um, One cycle time is taken by the CPU and access to the cache memory directly. So he's saying that access time in the processor spent 10 cycles waiting for the data. Okay, actually, usage of data is just only one cycle, right? From cache to processor. But 10 cycles are wasted in between. Wasted in the sense we made CPU to wait. So 10 cycles are being utilized by the memory system hierarchy to retrieve the data from main memory to cache. What cache method is needed to reduce the average memory access time to 1.5 cycles. Given the access to 1.5, what cache method is needed to reduce the average memory access time? Okay, 1.5 cycles. Okay, sorry. The best memory access is 1.5. The cache is 1. Instead of I don't know, I need to calculate that. But memory access, my memory is 100. So this 0.5, 500. So 5%. So this has to be reduced by 5%. Oh, wait, this is 0.5, right? So I'm surprised. Why this is 0.5? Yeah, so this is 0.5. The misrate is charge access time is 1 plus 100. Shifting this time to 1.5 and solving as a word of caution, performance improvements might not always be as good as they sound. For example, making the nervous system 10 times faster will not necessarily make a computer programming complex. If 50% of the program's instructions are loads and stores, a tenfold memory system improvement only means a 0.84 improvement in program performance. This general principle of Amdahl's law, it shows the effort spent on improving the performance of system is worthwhile only if the subsystem affects a large percentage of overall performance of the end request. If only companies um, so what we are trying to do is for performance improvements, making the nervous system 10 times faster will not necessarily make the computer programmers okay. Performance increased only by 1.82 times. Right? And see what is the one second. So Hamza has been used by computer scientists more than 2 hours and computer as well. Right. Okay, like uh, let's say in a processor design, we have these data paths. So let's consider a data path from 1 to 40 Java flip-flop. And these data paths are uh, numerous. There will be numerous data paths in the entire computer design, processor design. So you pick out the longest data path, which is important. So time, the time taken by that longest path to transfer the data is the bottleneck for us. So we need to satisfy that time. So in a way, we cannot keep on increasing the performance of the design. It has some bottlenecks. It's the path we are representing. And that's why it's popular among developers because it offers a simple and efficient management potential for some performance. By identifying the bottleneck in a program or system, developers can focus their efforts on optimizing that particular component instead of wasting time working on parts that will have minimal to longest we'll just pick out that longest path and we will try to optimize it. Parallel processing and the original instance. Parallel is one of Gene Handel, an American computer scientist. Here he discusses methods of anticipating the constraints of parallel computing is one multiple processor cost and computer values to perform many tasks available. Although it was presented back in 1967, remains crucial basis for numerous computing principles and technology and continues to be utilized widely to this day. Amdahl's law is powerful that uh, predicts the potential speed increase in the completing task. Okay, it improves system resources while keeping the workload constant. Theoretical speed up is always limited by the part of the task that cannot be Okay. The base formula for Amdahl's is speed up of a process, proportion of a program that can be made parallel, and as the speed up factor of parallel portion. Your company has scheduled a meeting with three team members first thing in the morning. Each team member needs to go themselves to the coffee, but they can't start the meeting until everyone has arrived. Two of the sales members drive themselves to the coffee, and third teammate rides step by step. According to Amdahl's law, if the team wants to start their meeting earlier, then they need to focus on the performance of the cycle, even if one of the drivers drives faster than usual. There's still no way to get around the fact that they have to wait for the key second. Your company has scheduled a meeting with three members two of the sales members drive themselves to their office while the other teammate rides. According to Amdahl's law, if the team wants to start their meeting earlier, then they need to focus on the performance of the cyclist. Even if one of the drivers drives faster than usual, there is still no way to get around the fact that they have to wait for the bicycles for the meeting. So Amdahl's part is still like even though you have parallel cores processing on the same thing, for like after reaching a point, increasing the performance, there will be a bottleneck where one of the one of the core is having the critical part where it takes the longest time. So that cannot be improved after some extent, some point, after some point. So all the other cores have to wait for this bottleneck code. An online store has social media and they are expecting a huge surge in the traffic. To handle the increased demand, they have decided to add more servers to the system. While additional servers can help them handle the increased traffic, they are limited to how many spaces or key that will be the bottleneck. According to analysts, they need to focus on increasing web pages rather than simply adding new servers to help search. One of the main disadvantages of Android is that it cannot be applied to situations where problems are going off the therefore, any improvement in the system of continues to do investment balance. In addition, Android government account for unexpected things. And also is an important principle in computing and providing guidance when optimizing system performance. By identifying the bottleneck in a program system, optimizing that particular component of system time within the task. Understanding this law of purpose and efficient way to maximize potential for any data. We continue to do our work. Okay, caches. A cache holds commonly used memory data. The number of data words that it can hold is called the capacity. Because the capacity of the cache is smaller than the memory, computer system designer must use a subset of memory is created with cache. Cache is a hiding place, especially for concealing and preserving provisions or information. Concealing, preserving provisions or information. Okay, we preserve, like we make mango pickle and we preserve it for almost 1 year. That's it. So we hide the data in a place. It's a hiding place, uh, which is for a specific data, which is reserved for further use. Okay, it's a hiding place. It's a shelter. You can say that concealing, 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 concealing. Okay, so it's a good point actually. Not to jump. Life is a hiding place. especially usually sounds good to body use information in the process of attempts to access data. It first gets the cache for the data. Cache is the data in the memory. The cache is the process which is the data from the memory and places it in the cache for further use. The command the new data, the cache must replace old data. This action makes it essentially in cache is answering the following questions. What data is held in cache? How is data found? And what data is replaced in the cache? What data is replaced to make room for new data when the cache is full. Okay, when reading an exceptions, keep in mind that the time force reduced versions inherent spatial and temporal locality of data access is matched in most applications. Keep in mind that the time force these functions is the inherent spatial and temporal locality of data access in most applications. Caches are all caches use spatial and temporal locality to predict what data will be read. For program access accesses data in a random order, it wouldn't benefit from a cache. If it had been a random access from CPU, then there is no meaning in using this memory hierarchy cache. As we explained the following lesson, caches are specified by their capacity, number of sets, block size, that is the distributed block space sets, number of blocks, and degree of associativity. Although we focus on data caches, the same principles apply for fetches and instruction cache. So we are focusing on data, and he's saying that same principles will be applied for instruction as well. Data cache store operations are data cache store operations are discussed for bookkeeping. We are focusing on data cache for now, and for instruction cache, it is very simple. Questions. Data.
Hello, am I audible now? Mm, I think so. Previously, I have been using this Bluetooth, so there was a issue with the Bluetooth headphone. Now I have this JBL. What is this? Boyan one. So yeah, let's continue. I hope my voice is clear, but I assume there is some noise. We'll figure out this later. Mm, okay. Okay, what actually we are gonna be studying in near future is clearly mentioned here. What data is held in the cache. Okay, so cache though, like, cache is a memory, but it has a very limited size. So it's our primary task that what kind of data, like what data has to be placed in that cache. So that is our first question. And how is the data found? Okay, so basically, let's say there is no cache memory and there is only single memory, that is main memory, RAM, let's say RAM, and a CPU. So CPU just gives the address of our desired data. So we'll just go to that address and we'll just bring the data from that main memory. So, but now we have introduced cache memory, which is a hiding place for frequently used data. Okay, so how do we find this? Uh, like CPU requires some specific data. So how does this, uh, like, what to say? How do I put this? So how does the CPU finds this data in cache? Cache is different. Main memory is different. CPU only knows the address location of a particular data that it requires in the main memory. So let me be, let's say CPU, this is main RAM, main memory. So these are locations, right? So let's say my desired location is this one. So I know the address of this location, let's say address is X. So in X location, I have my desired data. So CPU calls out that address in these address lines. So actually, if there is no hiding place in between RAM and CPU, it would have gone directly to the main memory and the data will be fetched to CPU. But now we have a intermediate hiding place, which is a cache memory. So uh, this is comparatively smaller than a RAM, but we are using the same address. We are using the address to locate, access data in the RAM. Same address is used for cache also. So how do we actually find the exact location in the cache, exact data that we want? So that is the task. And so how it is being identified. Okay. So what data is replaced to make room for new data when the cache is full? Okay. there is another scenario where the cache is very limited, right? And even smaller than the RAM. So what if the cache is full? It has been occupied. Every location is occupied. Now I have a requirement of storing new data. New data has to be stored in the cache because this data might be used in future. It might be. So I need to place this data in the cache. For that, I need to clear some portion of the cache and place the data. So how is this replacement? Like we are replacing some data with this new data. So how is this replacement is being taken place? So what data is replaced to make room for new data when the cache is full, correct? When reading the next sections, okay, we are answering the spatial and temporal locality. Caches use spatial and temporal. One second. Okay. Mm. So when reading, okay. So why do we do all these things? So just because of this single thing, like these two things, spatial and temporal locality. Caches use spatial and temporal locality to predict what data will be needed next. If a program accesses data in a random order, then there is no benefit of using a cache. As we explain in the following, नहीं, live कर I sent you, no, cache memory. Same thing. I'm reading those book.
Okay. You are reading those blogs. Right now, when you set a certain thing.
ज़्यादा pages है ना, more than 30. So I thought I would get sleepy. So I started live streaming.
You didn't sleep last night?
No, I sent you in the morning itself.
Okay, that's book. Yeah, 30 pages.
From 10 a.m. I started reading.
Cache memories में तो SRAM ही use होता है ना basically.
Yeah, cache memory is SRAM. Because SRAM is
faster. That is why we use
fastest memory.
fastest. Yeah.
But that size is very big, na? 6 transistors.
SRAM like
and the designing भी बहुत critical है, मतलब noise margin का issue आता है.
That is why we are able to design.
So it is expensive.
Also the size is not that much as compared to design.
DRAM का density बहुत है.
बहुत ज़्यादा है. Have you stopped it?
No.
No one is there.
Only 100 subscribers. In that only might was 1 or 2, 3 members. Live on who watches live.
Okay. There anyone?
No one. I think no one is there.
I was searching for that AMBA protocol. In that system analog code, course part 2, those all protocols are AXI, AHB, AMD.
Everything is there.
Those are like AMBA protocols. Collectively.
But
there are some 2 protocols missing actually. ACP and CACC.
ACP.
Yeah, I don't remember the name exactly.
I know AXI.
AXI is there.
CHI.
CHI
is the part of AMBA. That is the most advanced and latest one.
Latest one. CHI is
AMBA
the CHI is the latest one. AMBA, you told me that. I thought that AMBA is a single protocol. You told me it's a collection of protocols.
Initial thing is APB. APB, AHB.
This is how you transfer your data to
bus
protocol.
Bus itself.
Bus. You design advanced, that AMBA stands for Advanced Microcontroller.
Bus architecture. We just design the FSM to control the bus.
Then I was searching for some RISC-V architecture. There were some courses, not that worth it to buy. In one video, they are covering the flow of SOC. Why are you doing this?
They just make the course lengthy. Looks like lengthy.
No, not lengthy. Not descriptive.
Like content should be.
Point. Like design part, I want. Basically, like how to design. There was no pipelining thing in that.
I think I once showed you one YouTube playlist.
For RISC-V? No, for RISC-V. Is there anyone?
Not exactly for RISC-V, but you can get to know how the instructions are implemented in HDL. Like you will get an idea.
You told me there are some instructions specifically for this. The design is also important. Digital design.
Yes, yeah.
L1, L2. L1 is the smallest,
748 KB. हाँ कुछ भी हो सकता है, but L1 is the least one. Least size.
Like the size is increased from CPU to the secondary memory. The size increased. Just give me the channel.
Onur Mutlu.
Okay. Who is the prof in
Europe or Arabian countries.
Okay.
But these are actually.
Can you guys hear me?
PPT presentation.
Is it good that microphone is on or off?
No problem.
I think it's off, right?
Micro.
But it's not live also.
कर in-depth low
Okay, it's
level
live
में
now. That's
जाके
what he says.
how
Okay, that's good. So at least we can start right now.
comparisons are done, add
Okay,
operation,
but this
in the
camera, I don't
domain
like
it
it,
is,
so
how it is designed.
yeah. Okay, just make sure
Macro
you
level
pull the
में
right
आता है.
to be involved, like because we're gonna
These
update
are
the PC.
those.
So what we're going to do is this.
How the instruction is being fetched.
So a PC, normally you would
and how
increment
it
it,
is,
right?
transferred to the instruction decoder, and the action will be done, that execution.
That is only on block level.
Actually, these are enough for behavioral coding. These are enough. For gate level, we need to know the block, what is
What a
there in
block.
the block.
What is there in the
For behavioral, these are enough. We'll just write the conditions, and if the conditions are true, we'll perform these. If it is false, we will perform other things. So this is the block level. We will implement only block level. That is behavioral coding. ये जो मेरा वॉलपेपर है ना, मेरा वॉलपेपर गेट लेवल का है. ये यू दैट ब्लॉक है ना, इस ब्लॉक में घुसे तो ये गेट्स दिख जाएगा.
देख रहा. This is 2.5D.
256.
No, 2.5D association.
2.5D
Architecture. This
मतलब
2D architecture, this 2.5D architecture. In 2D architecture, there is only one thing I just line that you work in taking a whole word. But in 2.5D architecture, you do byte-wise word.
Okay.
There's like address decoder, or like row decoder and column decoder.
Instead of picking single row, I'm
selecting
specific
it
byte in
is
a.
discussed in Rabi also. 2.5D. Like row decoder is also there, column decoder is also there.
Okay, he might have told that using SRAM wala.
Like in that 2D architecture, you just take a whole word, you active a whole word, and then you access bit. Okay. So you are taking a chunk of it, chunk.
Achha, road decoder itself is a 2D structure. Like there will be row
Everything
lines,
is 2D.
column
2.5D is also 2D, but you are
specifically I'm
by
mentioning.
not instead of activating those things, you just activated single. That is the main difference. 2.5D. 2.5D is actually used in cache, and 2D is actually used in 2D is used in cache. 2.5D used in RAM or ROM.
Yeah, in cache we'll just take out the entire row. We call it as block.
That is it.
But for CPU it requires only byte. 2.5D accessing wala 2.5D hai, but between the caches it is two-dimensional. And for memory, main memory भी 2D है.
Main memory 2D.
बार बार जाके लाना बहुत टाइम लगेगा. So we'll just take out the entire.
That is the thing. Just showing the channel that video. Just share me, I will explore. Like industry people learn from these things.
Yeah.
Your brother learn from these things. Or they get any resources from the company. Some
For
confidential.
system Verilog.
No, not for system, anything. If they want to
Actually, they got trained in the company itself.
They got trained. They got KT.
सिस्टम वेरिलॉग को हम लोगों ने पढ़ाया था सिनॉप्सिस वालों ने. For around more than 3-4 months.
4 months तक पढ़ाया.
At least 3 months तो होगा.
उनको पढ़ाया था प्रॉपर.
I think so.
Nice. उसके बाद क्या हुआ था प्रोजेक्ट?
हाँ, छोटा प्रोजेक्ट दिया था और maybe
during internship this is
for 13 months internship.
Okay, then like
Full time.
easy क्या हुआ? Chill time.
मतलब if you like coding,
how much they are giving you in that 30 minutes?
I think we should stop the mic.
That is design SRAM as quick as possible because I know ना SRAM like design करना
SRAM is simple, but for a first time listener who is learning it for first time, it might take some time.
Then I will move to DRAM because time constraint is very
मैंने like कल भी देखा था कि DRAM में थोड़ा एक्सटर्नल सर्क्यूटरी भी है, चार्ज पंप करने का,
charge pump
हाँ
mail wise design में charge pump
हाँ, ये सब करने का थोड़ा एक्स्ट्रा सर्क्यूट्स भी है SRAM के, other than SRAM वाला सर्क्यूट्स, bright circuits and XAMPP. These extra things are there for DRAM. Just it will take 1 day to get the proper feel. DRAM is the base for DDR4. DDR4 itself is a DRAM.
DRAM is the base of DDR. Yeah.
So these are very industry standard names.
Yeah.
If we mention these in resume, they would expect a lot.
Like
So it's not bad that they would expect a lot.
no, we are
At least
fresher,
we have
We
tried
know.
industry standard projects and we have got some knowledge. It's
not
not like
up to
we
the code.
answered.
If you don't know, like we don't know, we will try to answer.
It's
the
not
question.
bad that we answer every question.
हाँ
It's okay to answer half of the question at least.
50% 60% hit कर लोगे तो होता है because still like electronics engineers are very less because BTech करके तुम भी जान लो क्या होता है. If you are BTech electronics engineer, you don't know nothing. If you are not from IITs,
Yes,
you know nothing.
I am the example.
Me too. When I was in I spent
But
2
at least I
hours.
got to know from 7th semester. I started to know everything.
Like I learned the basics, but implementation part was not done well. Where I was designing small stuff, getting things, some combination circuits I was now working on some sequential with some sequential cells also like DFT clock and matches design with spice also. Going to some that thing also. S27 benchmark circuits, consistent sequential system, delay leakages, dynamic power strategy, these things. Process variation, how to do this. So I get to know these basic stuff. Then from designer part, like digital part is a lot. Like DFT is different. DFT is a different.
That is different.
I cannot target DFT. DFT is tough. That is a class actually. You cannot do DFT by your own self because the industry is way ahead. If you match the DFT build.
इसमें बहुत ज़्यादा creativity होना चाहिए.
बहुत creativity होनी चाहिए.
क्योंकि test cases ढूंढना बहुत difficult है.
बहुत.
You need to understand design properly. Then
How
you need to create the test cases. On your
like
own.
यहाँ पे ये fail होगा.
हाँ.
That will take time.
That is ahead of a designer.
That is first focus on design, then go to fault coverage and this.
लंच करने जा रहे हैं.
तो मैंने बनाना कर लिया सर.
I ate that oats वाला.
Yeah.
I ate oats.
Okay. अभी वही खाओ भाई. मैस में मत खाना.
Banana grapes मिला के खाएं.
मैस में मत खाना. मैस.
I stopped eating for 2 days.
मैस एकदम.
कल भी नहीं खाऊंगा.
एकदम छोड़ दो अभी. नहीं बाहर से खा लो. If you are ordering something, you can order it from the JDM Punjabi Dhaba.
Okay, JDM Punjabi Dhaba.
Like the price is affordable and the quantity is good. And the food is also quality is good. JDM Punjabi Dhaba.
JDM
Punjabi Dhaba. Like we ordered yesterday aloo ka paratha. You eat aloo ka paratha. Aloo ka paratha like 130, 140 something. Too big this size. Pizza size aloo ka paratha. You will get one chutney and one curd. Sweet curd. That's it. In place of chutney, you can order pickle also. You can from 8 rupees you can order one butter.
Okay.
You will get like your stomach will get 2 paratha. Or there are a lot of parathas like methi paratha, cheese paratha is also there. The price is like very good. 70 rupees per paratha.
One paratha is itself.
Like I ordered a meal actually. I ordered roti. You know roti, no? Chapati. So chapati is also the same size as well.
Usually it is small, na?
But
Yes,
they are Punjabi, na? They make everything big. Punjabis are like
Cow.
cow, cow. Have you have like any Punjabi friend?
No.
No, if you have, you should.
Anshul Sharma is Punjabi,
No,
right?
he is not Punjabi, not a pure Punjabi. Pure Punjabi means that guy who
Acha.
Saudi man.
If he is a pure Punjabi, he must have.
Punjabi, the Munda Punjabi.
Hmm.
They don't wear turban.
Okay.
There is Punjabi who wear turban.
Hmm.
There is Punjabi who wear something not turban, but they cover their head like this.
Okay.
Their belief system is like different
Hmm.
ideas. Okay.
Bye.
Bye.
Hmm. 1 minute. Okay. So where were we? Okay, we were talking about spatial and temporal locality. Okay, yeah, this is at another important point that actually program accesses data in random order, but if it had been not in a sorry program like CPU actually access data in some pattern, okay, address by address that are stored like address locations are that are adjacent in nature. So those will be accessed by the PC, CPU, core, whatever. So if it had been a random order, then inclusion of cache, this memory hierarchy is useless. Okay. As we explain in the following sections, caches are it is streaming and the audio is on. Okay. As we explain the following sections, caches are specified by their capacity. Capacity in the sense the memory size. Okay. Let me use this. Capacity, number of sets that is related to set associativity, I guess. Block size, and this is line length, like one row size in case in a cache, number of blocks, number of lines, okay, and degree of associativity. Okay, okay. So number of sets. Let's say there are 8 lines of cache, and degree of associativity is 2. Then number of sets will be 4. Log 8 base. Actually, wait. 1 okay, a plus 1 करो हो जाए. If you have 16, half base to 4, decrease to, okay, you cannot that into. Let's leave it for now. I know something about associativity and number of sets, block size, this capacity, because I have covered some prerequisite stuff. So I have been following Anuj Grover sir, and in this memory design course, wait, maybe it is not selected. I studied SRAM, then I started cache memory. So if anyone is interested, you may follow Anuj Grover sir. I strongly recommend his lectures. You just see one video and get to understand why. So I studied these, and I just want to get more insights towards the cache, what is cache and how it is being implemented. Also, I have also covered, but he covered as much as it requires for DRAM operation and all. I even want to solve some numericals on cache problems. Okay, that he is not, because this course is more about the designing. So we just need to cover the design. Although we focus on data cache routes, the same principles apply for fetches from an instruction cache. Okay. We have basically, we may have two kinds of caches. One is for data and one is for instructions. So we are actually currently discussing about data cache. this one. So he's saying that same principles would be, will be applied for instruction cache as well. Data cache store operations are similar and are discussed further in 8.3.4. Okay, we are actually loading. Okay, wait, although we focus on data cache loads. Okay, data cache store operations are similar. Discussed. Okay, got it. Actually, we are now we are actually we have this cache and main memory and the CPU. So we are actually loading, right? Okay, we are actually loading the data. So there would be some conditions where CPU wants write data into the cache. So that is a different thing. So that will be discussed in 8.3.4. Yeah, this is storing the data into the memory, and this is loading. Okay. Load store. What data is held in the cache? Okay, what data is held in the cache? This is the question that we have been waiting for. So what? Let me use another color. This is bad. What data? So an ideal cache would uh, anticipate all of the data needed by the processor. Wait, ideal cache would anticipate all of the data needed by the processor and fetch it from main memory ahead of time so that the cache has a zero miss rate. Because it is impossible to predict the future with perfect accuracy, cache must guess what data will be needed based on the past pattern of memory access. Okay. Okay, let me put it this way where okay, let me think. Let's say you have a main memory where you have loaded PUBG game. Okay, so in memory we can say that in location 0 that game interface has been loaded, the initial login page, and in location 1 sign up or login जो होता है ना, like we do have this other links if we want to log in through Facebook or Google, so those links will be there. So somehow you logged in and you entered the game interface start button, that interface at location 2. So at location 3 you have like you have some branching operations. Okay, first branch will lead to, let's say, training grounds. Second branch would lead to some war zones. Okay, so third branch so this training ground contains a lot of data. That is a branch. And this what do we say, let's say war zone contains a lot of data. And then let's say Arangel, so that map will have some more data. and you may say weekend will have some more data. So there is a cache, there is a CPU. So CPU is currently, let's say, it is at the opening start page, like not start page, like opening interface, location 0. So what cache should have? So it might have already taken all these things till start. Okay, so I have 0th location, first location, second location. So it has been processed. These 3 locations are processed, and based on the pattern that we have been seeing in the cache memory, he has opened PUBG, logged in, and he has entered start interface. So with this previous history, cache memory should be knowing that he would use these uh, either training ground or Warzone or Arranger map or weekend anything. So in a way, cache should be able to load training ground data and Warzone data, Arranger data, weekend data, something like that. If CPU asks for Warzone, so it will fetch all the data, at least some data related to Warzone. So now Warzone is being implemented on the CPU. So the history would, what the cache memory access history would tell is CPU has access to Warzone. So I need to bring all the data in the Warzone, whatever the data that is there in the main memory. So it will bring out all the data that is related to Warzone. So I have entire Warzone data. There will be some locations where we have some exit options, that branching programs or some other utilities. Yeah, this is CPU. If you get exit, you need to get another kind of cache data. That is again this var arranger, something like that. So CPU works like this cache memory system. So based on the track of previous access, we would get the next data accordingly. So an ideal cache would anticipate all of the data needed by the processor and fetch it from main memory ahead of time. So it cannot fetch entire data into the cache by predicting the future usage of CPU. So we try to bring like most usable, most probabilistically mostly usable data into the cache, so that get a good hit rate, less miss rate. So because it is impossible to predict the future with perfect accuracy, cache must guess what data will be needed based on the past pattern of memory access. Okay, this has to be highlighted based on the past pattern of memory access. Guess करना है. In particular, the cache exploits temporal, okay, time wala, temporal and spatial locality. It exploits temporal and spatial locality. These has to be temporal, spatial locality. Recall that temporal locality means that the processor is likely to access a piece of data against if it has accessed the data recently. Therefore, when the processor loads or stores data that is not in the cache, the data is copied from main memory into the cache. Subsequent requests for the data hit in the cache. Okay. If there is a mess, we will just copy the data from main memory into the cache. Subsequent requests for that data hit in the cache. Okay. We in a we bring the data in such a way that the further subsequent requests from the CPU will be a hit data hit. Recall the spatial locality means that when the processor accesses a piece of data, it is also likely to access the data in nearby memory locations. So let's say if it has accessed this location, then there is a lot of chance to access these locations as well. So we'll bring this entire chunk of memory. Sorry. Okay, therefore, when the cache fetches one word from memory, it may also fetch several adjacent words. This group of words is called a cache block. So whatever we fetch along with that single word, those adjacent words हो जो है ना, like while we fetch the specific word from the main memory. Besides that, whatever we fetch the adjacent addresses, those are called as cache block. Okay, this is called as cache block. Memory management. Okay, cache fetches one word from memory. It may also fetch several adjacent words. The number of words in the cache block P is called block size. Okay. Block size. A cache of capacity C contains B equals to C by B blocks. So it has some C capacity. So if I want to know number of blocks in that, then I will divide each block size. I'll get the number of blocks. So principle of temporal spatial locality have been experimentally verified in real programs. If a variable is used in a program, okay, the same variable is likely to be used again, creating temporal locality. So if I, let's say, write a C program, let's say I'm writing a C program. There is a variable A and variable B, and I'm doing some operations. So first place, int A instruction is being loaded into the CPU. Since cache has received in variable A, which is int type, and it is being used by CPU, it is more likely that the CPU might use this variable A in future as well. So this is temporal feature. Okay, so we need to keep this A in the cache itself. So to exploit the temporal temporal locality, क्या सकता है क्या? Same variable is likely to be used again, creating temporal locality. Yeah, correct. If an element in an array is used, Okay, if there is an array and we have used a element in that. So it is likely that we might use the other elements in that array. So it's good that we bring the entire array into the cache. Other elements in the same array are also likely to be used, creating spatial locality. Okay. Previously, that is a program, variable a is there, and we might be using that in future. So this is temporal. Spatial is different. Like you have an array, you have accessed this array of 0, and it is most likely that you might use this entire array. So you are just in a way bringing entire array into the cache. This is spatial property. Caches are okay. How is data found? Okay, we have studied what is like what data is held. Okay, we exploit temporal locality and spatial locality. This is what kind of data, and we now need to know how data is found. Okay, so I'll create another page. Else I would get confused. How is data found? This is 8.3.2. Okay, 8.3.2. A cache is organized into assets. Okay, each of which holds one or more blocks of data. Relationship between address of data in main memory and the location of that data in the cache is called mapping. Okay, good. Like in main memory, we have some set of addresses, some finite fixed number of locations. Let's say there is a memory 32 by 32. These units are in bytes, let's say. Okay, so 2 power 5, 2 power 5, 2 power 10, which is 1k, 1k, correct? 2 power 5, 2 power 5, I'll get 2 power 10, which is 1k bytes. If each of these unit is a bit, then it is 1k bits. So if you divide 1k bits by 8, you'll get bytes. So that is nothing but around 2 power 7, 128 bytes. So cache is organized into assets. अनुज सर ने ये बोला था कि okay, he started from the scratch and okay, let's see. Delete. A cache is organized into assets, each of which holds one or more blocks of data. Okay. I need more colors. So, no, it's a good practice that we keep an hierarchy. Okay, so this is cache. Oh my god. This is cache. These are blocks. Block in the sense we talked about cache block. So instead of bringing one address location, we bring adjacent locations as well. So that is cache block. Number of the size of the block is decided by the OS. Okay. So let's say this is the cache block 0, 1, 2, 3, 4, 5, 6, and so on. So he's saying that there are some sets organized in sets. Okay, I may, like there are six, right? Okay, I may uh, I may design cache in such a way that there are for one set there are two cache blocks. So this is the thing, and there are plenty of blocks for the I didn't mention. So this is a set. So set can have any number of blocks, even one block also. The relation between the address of data in the main memory and the location of the data in the cache is called. Okay, let's say I'm accessing location somewhere in the middle. Okay, some X row, some Y column. So this location, but okay, there is X comma Y location is there in this cache somewhere, but as we know, this main memory is 32 by 32 and cache might have not been that much big. Cache would have been some smaller size memory, let's say 8 by 8. So how do you map this? Like, let me be clear. Like you have CPU. CPU sends the address that specifies location in main memory. Okay, so if the address is specifying the location in main memory, which is 32 by 32 bytes, it would have been fine to access it from main memory, but we are trying to access the data from cache, right? Cache is not 32 by 32 bytes, so I cannot use this address directly. I cannot give this address directly to column decoder, row decoder, and find the location, right? So there should be some mapping between main memory and cache memory, like a relation that is called mapping. Address of data in main memory and location of data in cache memory. Nice. So we have limited colors. Okay. So address of data in main memory, location of that data in cache is called mapping. So relation between them. Each memory address maps to exactly one set in cache. Wait, each memory address maps to exactly one set in the cache. Some of the address bits are used to determine which cache set contains the data. If the set contains more than one block, the data may be kept in any one of the blocks in the set. Okay. Okay. He's saying that. Let's say you have a cache. So let's say this is a set. Let's say set 0. And there are two blocks, block 1, block 0. So one of the address bits selects these two blocks. I mean this set 0. So those bits will select this set 0, and the data either reading or writing. Now we are focused on reading, right? Okay, let's say write. Okay, I have this data D. So this data D can be put in block 1 or block 2, I mean block 0. So either of these blocks can be occupied by data D, and if I want to like store this data D into one block, then I need to, so in a way I'm just removing the older data, right? The data that is previously been stored in this block. So that data is being replaced. Okay. So there are some replacement rules where according to some methods, let's say LRU, least recently used. If block 1 is least recently used, then it might be that it wouldn't be useful as much as block 0. So it's better to replace block 1. So I'll replace block 1 with data D. So somehow that replacement, according to some replacement policies, the data will be, newer data will be replaced by the older data. And there are some sets, right? So that is the thing. Caches are categorized based on number of blocks in a set. Okay, एक सेट में कितने blocks हैं? In a direct mapped cache, okay, according to the number of blocks in a set, these things are classified. If the number of blocks are 1 in a set, then it is called direct mapped. So the thing is, if there is only one block in each set, then that is called direct mapped cache. So the cache has S equal to B nets sets. Set equals to B sets. B is actually number of blocks, right? So number of sets equal to number of blocks. Thus a particular main memory address maps to a unique block in the cache. In an n-way set associative cache, each set contains n blocks. 1 second. This direct mapped caches, its set contains particular main memory address maps to a unique block in the cache. Okay. Okay. So I'm not liking the colors now. Okay. So if sets set contains one block, only one block, cache block, then it is called direct mapped cache. So why it is called as direct mapped cache? See, if you have 32 by 32 bytes, then there will be 5 address lines in the row, like 5 rows, 5 columns. Actually, like these will be actually given to some decoder. That decoder will generate 32 lines. This as well. These 5 lines will be given to decoder, or actually in SRAM we call them as analog mux multiplexer, column multiplexer. These 5 lines will be given to column multiplexer. We'll get 32 lines. So in a way we are at a time selecting 1 byte among 1 kilobytes. 1 किलोबाइट्स में हम 1 किलोबाइट सॉरी 1 किलोबाइट में हम 1 बाइट को सेलेक्ट कर रहे हैं अकॉर्डिंग टू द एड्रेस. So if I have 32 by 32 locations, then I would be having 10 address bits. 4, 5, 6, 7, 8, 9, 10. So these are my address bits A0 to A9, A0. So with these 10 address bits, I can access any single byte in 32 by 32 bytes main memory. So let's say now let's come to cache. Let's say cache has only a size of 8 by 8. Okay, I have a cache memory of 8 by 8. uh, 8 by 8. That in the sense 3 lines goes to row, 3 lines to column, and I will be having 8 rows, 8 columns. So in a way I have 64 locations. Here I have 1 kilo locations, 1024 locations. In here I have 64 locations. So how do I map this address into this cache? That is the question. So basically just take the LSB. You need how many? 6, right? So take the LSB 6 bits, A0, A1, A2, A3, A4, A5, and give those to A's. Okay, so basically we give those to A5, A4, A3, A2, A1, A0. So you will pick up one location. Okay, so let's say that location contains actually this becomes a little complicated because I have skipped some information. So actually in cache, how the data is stored is that is different. You don't actually have the data itself. You have some other stuff as well that are used to determine whether this data is being picked up from particular location that tells that it is valid. Okay, CPU, it is talking to CPU. CPU, you are asking something, and I have the verification, some verification identity, some code. Please check it. If I am correct, then take me. It is a hit. If it is wrong, then it is a miss. You can go to some other higher level of memory. You can get those. Actually, CPU doesn't do this. Software actually takes all the hectic work. CPU goes to some other task. This comparison will be done at every axis. So we'll see these. So this is the thing, like we have address of this 32 by 32 byte locations, and this is smaller size cache memory. Then how do you find the location of that data using this 10-bit address? How do you map it? What is that relation? So the cache has S bits. So sorry. Let we have some water. So thus we like what to say, does a particular main memory address maps to a unique block in the cache. Okay, in a direct mapped cache, it is okay, it is a direct map. It uniquely chooses a single block in the makes sense. So what we just studied is there is a direct mapping. Let's say this is the cache. And there is a set of two. Okay, two blocks. Let's say this is address location 0 and there is no requirement for the column, right? We play with the blocks in the cache, so there is no requirement for the column. But CPU, when it comes to while giving the data to CPU, we need to give only a specific number of bits. If it is an 8-bit processor, we have to give only 8 bits. Okay, so what selection is there? A lot of things are there. So let's say when it comes to rows, address location 0 corresponds to 2 blocks of cache. It's not one, it's not unique. Address location 0 can go to this block or this block, so this is not unique. Unique कब बनता है कि when the unique nature comes into picture is when you have each cache block has associated with only one set. So set 0 has only one block. So this is a set 0. Set 1 is address location 1. Set 2 is address location 2. Something like that. There is no grouping thing. So you can uniquely access each block in the cache. That is direct mapping. Does a particular main memory address maps to a unique block in the cache? Okay. In an n-way set associative cache, okay, basically direct mapped is something one-way set associative cache, but we are now discussing about n-way set associative cache. Each set contains n blocks. Okay, so that is the thing. Set of like 2 set associative cache is something that has n 2 blocks in a set. The address still maps to a unique set with s equals to number of sets equals to number of blocks by set size, number of blocks in a set. But the data from the address can go in any of n blocks in that set. A fully associative cache has only s equal to one set. Okay, Um, okay, okay. Data can go in any one of the B blocks in the set. So there is only one set in the cache. So we are in a way considering entire cache blocks in a single set. So the incoming data can go anywhere in the cache. This is fully associative. Sorry, excuse me. Hence, a fully associative cache is another name for a B-based set associative cache. B is nothing but number of blocks in a cache. So let's say there are 8 blocks in a cache. So 8 set associative cache is fully associative cache. To illustrate these cache organization, we will consider a MIPS memory system with 32-bit addresses and 32-bit words. The memory is byte addressable and each word is 4 bytes. Okay, so the memory consists of 2 or 30 words aligned on word boundaries. We analyze caches with an 8-word capacity for the sake of simplicity. We begin with 1-word block size, then generalize later on to larger blocks. So there is some stuff related to direct mapping. This cache fields. This is set. Temporal locality cache block conflict. Okay, fully associative. Okay. Spatial locality with the okay. What data is replaced? Okay, fine. Yeah, next 7 pages or 8 pages related to this fully associative, direct mapping, set associative, all these things. Then there is replacement policy. Yeah. So after that, we go to writing the data into the cache. So that is a small portion, I would say. Then I should be checking answer lecture. I didn't cover the write operation. And then he went to virtual memory. Virtual memory is the you would say lower level hierarchy, lower level memory system in the memory system hierarchy. Okay, hard disk. So hard disk has, man, it has got a lot of stuff. Paging. Okay. So then there are some numericals, right? Oh, you have IO as well. IO is a mapping. So we are here right now. Here. So he has given some context before entering the discussion that we are going to be discussing about a MIPS memory system with 32-bit addresses. Give me some few minutes. It takes Hello. Let's continue. Mm, okay. So constraints are, so we have a MIPS processor that has 32-bit addresses and 32-bit words. Like each and every location contains 32-bit. So each location is considered as a single word, and single word contains 32 bits. Okay. The memory is, let me highlight this, might come handy. 32-bit addresses. The memory is byte addressable, so I can pick up a single byte among the 4 bytes, and each word is 4 bytes. Okay, so the memory consists of 2 part 30 words aligned on word boundaries. Okay, so we're saying that uh, mm, okay, so let's say it's not byte addressable, it's word addressable, then I could have only have how many, like I could have 2 power 32 words, correct? Or is it wrong? Let me check. 32-bit address in the sense 2 power, man, this is so light. 2 power 32, that is 2 power 10, 2 power 10, 2 power 10, 2 square. So 4, this k. 4 gigs, 4 gigs, massive. So each location, is it a byte or bit? So since it is a byte addressable, we may call it as byte. 4 gigabytes. So since I have 4 gigabytes and byte addressable, word is 4 bytes, so now I can decide to go 13 words and then on 4 boundaries. Okay, I would say 2 power 32 bytes aligned on the word boundary. Let's say so. This is 1, 2, 3, and so on. I have around 2 power 32. Okay, but he's saying that 2 power 30 words. So each word contains 4 bytes. So I have to reduce these words, like these block count by 4. By 4 in the sense I have to divide the number of blocks by 4. So 2 power 32 divided by 4, which is 2 power 30. So that is how we got 2 power 30 words. So aligned on word boundaries, we analyze caches with an 8-word capacity. 8-word capacity for the why am I like okay? We analyze caches with an 8-word capacity for the sake of simplicity. We begin with a 1-word block size, then generalize. So we have talked about cache blocks and addressing them and how the main memory address is related to the cache memory, how the data is found, right? So for the sake of simplicity, we are just considering 8-word capacity. Okay, this is actually okay, 8-word capacity in the sense we could accommodate only 8 words in the cache. Okay, clear? So for me it's clear. We begin with 1-word block size. Okay, so one block size is 1 word. Okay, and the capacity is 8 word. So each block, like number of blocks will be 8. Each block contains 1 word and the total capacity is 8 word. So the number of blocks will be 8. Okay, correct. Then generalize later to larger blocks. Okay. Shall I remove these? Okay. A direct mapped cache has 1 block in each set. Wait, direct mapped cache has 1 block in each set. Okay. Yeah, I forgot that. Yeah, 1 block in each set. So it is organized into S equal to B sets. To understand the mapping of memory addresses onto cache blocks, imagine main memory as being mapped into B word blocks, just as the cache is. An address in the block 0 of main memory maps to set 0. Okay. Of the cache. An address in the block 1 of the main memory maps to set 1 of the cache, and so forth, until an address in block B minus 1 of memory maps to block B minus 1 of the cache. There are no more blocks of the cache. So mapping wraps around such that block B of main memory maps to block 0 of the cache. Okay. So it again wraps around and comes to the initial block 0. So he's saying that so what did we say? So imagine main memory like mapped to B word blocks. Okay, what is this B? So block size. Okay, I need to highlight this. Map memory ultrasound. pivot blocks. Okay. Now things are getting cleared slowly. So this is main memory, right? Let me make it big. Okay, let's say memory has it has some blocks. Okay, some block y, some block y minus 1, such that this is block 0 and this is block 1. Correct? So each word is 8-bit. Correct? Actually, size is b. Size is b. Block size is b. And actually, this is main memory. Size is b. So just as a caches an addressing block 0 of main memory maps to set 0. Okay, excuse me. Block 0 of main memory maps to set 0 of cache. So I need to draw a cache as well. Let's say there is a cache. Let me do this tensor right. Actually, that is big. No problem. So this is B block size, same block size. Okay, let's leave it like this. B an address in block 0 of main memory maps to set 0 of the cache. Okay, let's say this is this address location 0. So address in block 0 of main memory. Okay, block 0 of main memory maps to set 0 of cache. It's good to have a different color. So this maps to set 1. Set 1 in the sense set 0. An address in block 1 of main memory maps to set 1 of the cache. Okay. Okay. So in block 1, it addresses the set 1 and so forth until an address in block B minus 1. So this is okay, this is actually block Y, right? So in the midway there is a block that is b minus 1. So here you have this block b minus 1. Okay, so if we are talking about direct map, then there will be only one block for each set, right? So then there is no need to mention these many chunks of blocks for each set. I could simply mention a single block itself. So this is set 0 and this is set 1. So this thing is pointing to set 1 and so I have another block here. So this block actually is pointing to this one. There are no more blocks of the cache, so the mapping wraps around. So for now, main memory and cache memory are being mapped, but further, if we go further, then there is no space for data to be stored in cache. So we have to wrap it around and we have to point to the base again. This is called wrapping, such that block B of main, so block B of main memory so block B of main memory at the rate B maps to log 0 of cache. So it maps to set 0 or log 0. This mapping is illustrated in 8.5 for a direct map cache with a capacity of 8 words and a block size of 1 word. So capacity is 8 words and block size is 1 word. So there are 8 blocks. The cache has 8 sets. Yeah, each set contains only single word, each of which contains a 1 word block. The bottom 2 bits of address are always 0, 0. The bottom 2 bits of the address are always 0, 0 because they are word aligned. The next 3 bits indicate the set onto which the memory address maps. Thus, the data at addresses 100 and 24. Okay. So 4 and 24 Direct map cache. Okay. So what did he mention? I forgot. Okay, each. We know this. So zeroth location is mapped to set 0, and this 100 thing is mapped to set 1, and 100 is there, but that is the thing. So bottom, so address are always 00. Okay. So 100. In between there are 4 words. Where am I missing? Okay, in main memory. 1, 2, 3, 4, 5, 6, 7, 8, 32. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, now it makes sense. So actually this block, this main memory, each block is 32-bit wide, and the cache is actually 8-bit wide. Okay, what we are doing is, in these 4 bytes, let me draw those so that it would be clear. Actually this is wrong. Wouldn't say wrong, but kind of wrong. Let me tell you what it is. So what I thought is, main memory contains each block 8-bit. So there will be 2 power 32 lines, 2 power 32 blocks. So but it's not the case. As you can see here, 32-bit addresses, 32-bit words. So Excuse me. So actually, let me redraw this. This is main memory, and he told that this length, right? This length is 2 power 30 words. Okay, and this one is one word of main memory that is equal to 32 bits. Okay, so what am I doing is so this is one block of 4 bytes. This is another block of 4 bytes, and so on. Some block B of 4 bytes, and so on. Like that, we have 2 power 30 blocks. Okay, this is byte 0, byte 1, byte 2, byte 3. This will be 0, 0, 0, 1, 1, 0, 1, 1. So lower 2 bits are fixed. If you can see here, a direct mapped cache has one block in each set. So it is organized into B sets. To understand mapping of memory addresses onto cache blocks, imagine main memory as being mapped into B blocks. Okay. B blocks just as the cache is. Wait. B word blocks. So this is B word blocks. Just as cache. Okay. So this is actually cache. This single thing is B. Got it. One block, one of main memory. Wait. Just as cache. And address in block 0 of main memory. Okay, this is block 0. This is block 1. This is block something. Okay. This top one will be block 2 power 30 minus 1. So block 0 of main memory maps to set 0 of the cache. So this one, we could write this as this one, and an address block in block 1 of main memory maps to set 1 of cache. So block 1 maps to this one. Block B minus 1. So let's say block B minus 1 yeah, B b minus 1. There are no more blocks of the cache. There are no more blocks of the cache. So the mapping wraps around that. Such that block B of main memory maps to block 0 of the cache. So actually we are just pulling out this code. And in this one, b plus 1 maps to block. This is again, you could say 2 of b minus 1. Let's say 7 and that 15 that. Okay. 2b minus 1. 2b minus 1 maps to this one. So this is how cache gets mapped to main memory. Okay. This mapping illustrated direct map cache with the capacity of 8 blocks and a block size of 1 word. The cache has 8 cells, each of which contains 1 word block. The bottom two bits of the address are always 0. Okay. Because they are word aligned. Next, 3 bits indicate okay, there are 8 cache blocks, right? So we need log 8 base 2 bits to map them. So the set onto which the memory address maps such that data address at default. So if I just make an abstract view of this, this is my main memory and there are 4 columns in it. So I'm just mapping the first column onto the cache memory. Okay, so cache memory is of course small, and it has to be mapped to main memory. So let's say there are only 4 locations. So it will be mapped like this. Then this, then this, correct? Then for the next location, so this is pink and white. So this is how this entire column gets mapped to this cache memory. Why did we only left the last 2 bits? That's my question. Because we have only 4 columns here. Let me mark these up there. So this is 0, 0, 0, 1, 1, 0, 1, 1. So actually, when we access a single column of a main memory, which contains 4 columns, least 2 bits will be fixed for a single column. So there is no use of utilizing those 2 bits. They are fixed 0, 0. So then later on, based on the size of the cache, let's say I have 4 blocks of cache. So then I need log4 base 2 number of bits in the address, that is 2. So I just need to fix least 2 as 0, 0. Then I need these 2 to kind of associate map things from main memory to the cache memory. So that is how it is done. If it had been 8, then I would have required 3 bits. Okay. Okay. 0 E4 match to set 1. Acha, okay. 24 E4 or match to set 1. Correct. As shown in blue. Likewise, data at address 10 FF0. Okay. FF0 also set 4. Acha, 10 100 F0. Okay. Hi. I just got. Okay. Set 4. And so what? Okay. Each main memory address maps to exactly one set in the cache fields. Okay. To what cache set in figure 8.5? Okay. Does the word address 14 map name another address that maps to same set 14? So over 2 bits are 0. This is 1 0. So 101. 101 is 5. 101 is 5. So 10 001. Okay, 101 set 5. So set 5 will be, yeah. So where else I would get 101? 4. Because many addresses map to a single set. Okay. Because many addresses map to single set, the cache must also keep track of the address. Okay, because many addresses map to a single set. Acha, एक set, like one set gets, see here, one set is getting 0th block, I would say, 0th block of main memory, and even 4th block of main memory. So that's the thing. So we need to keep track of the address, right? And address of the data. Actually, besides bringing the data, it should also carry the address of the data. Least significant bits of the address specify which set holds the data. Okay. The remaining more significant bits are called tag and indicate which of the many possible addresses is held in that set. In our previous example, two less significant bits of 32 are called byte offset because they indicate the byte within the word. The next three bits are called the set bits because they indicate the set to which the address maps. Okay. In general, the number of set bits is log s base 2. So we have 8 sets. So it will be 3. The remaining 27 tag bits indicate the memory address of the data stored in a given cache. So figure 8 shows the cache fields for address. It maps to set 1 and its tag is all 1. 0100 and the other, okay, it requires 5 bits, right? 0100 goes for that and E0 is everything 0. Okay, this one. Set 1 byte 0 cache fields. Find the number of set and tag bits for a direct mapped cache with 1024 okay sets and one word block size. Example 8.5 direct mapped cache. So it has 0, 1, 10, 23 and a one word block size. Okay, one word. The address size is 32 bits. So address size is 32 bits. 31 0. ये तो tag हो गया, ये तो set. This is offset byte. So number of set and tag bits for a direct mapped cache with tag sets. So in order to map 1024 sets, I need 10 lines. So set bits are 10 and tag bits. So in order to get tag bits, I need to know offset bits. So under one word block size in the sense it might be okay, let's say main, if he is talking about main memory one word, then then the entire row is kept here, right? Okay, but we are talking about this, like these will be two zeros or 0 1 or 1 0 or 1 whatever. So 12 I will be left with 20. A cache with 2 or 10 sets requires 10 set bits. 2 least significant bits of the address are byte offset and the remaining 32 minus 10 minus 2 will be 20. in the tag. Um, Sometimes, such as when the computer first stops up. Okay, I need few minutes of break. So sometimes, such as when computer first starts up, the cache sets contain no data at all. The cache uses a valid bit for each set. Okay, when the computer starts up, there will be no data in the cache. Okay. The cache uses a valid bit for each set to indicate whether the set holds meaningful data, whether the cache set holds the meaningful data or not. Okay. If the valid bit is 0, the contents are meaningless. Okay, if it is 0, then it's useless to read the data or what? We shouldn't read the data into CPU. Shows the hardware for direct mapped cache of figure 8.5. Is figure 8.7. Where is figure 8.5? Okay. So this is clear, right? Where did we fix this lower 2 bits and convert the other 3 bits? It's because just to I mean, what would we say? Like, maybe it's because of since I have done that answer course, he mentioned about burst mode. So since in memory each block there are 4 bytes. Mm, So there are 4 bytes in each block of main memory, right? So if I let's say processor requires 0th location, 0th byte. So instead of like besides bringing this single byte, I would anyway have selected this row. So since I have selected this row, there will be some muxes, right? So since I have selected this row, मैं फट से ये 4 bytes को ले सकता हूँ ना. I can read all the 4 bytes using the mux. So the least 2 bits are used to switch these muxes. So in a way, I can place them here. Then the cache block size would become 32-bit, which is 4 byte, one word of main memory. So that is burst mode. Then I can go to the next row. This also goes to next row. So these two get mapped. So this flip-flop will be enabled to receive the data. This flip-flop is able to give out the data. Then FAT say 4 as well. That's the thing, I guess. We should only go for initial things. Could be okay. And if what if the PC needs first byte of 0th row? Then there is no possibility of bringing this. We'll just take these because these might have been already used or something else. This is actually, I would say, line size, line length, and fetch width. We'll see. I'm just complicating everything. So this is how things happen. Sometimes, such as when the computer okay, shows the hardware for the DirectNet cache 8.5. The cache is constructed as an 8-entry SRAM. Okay. Right. Excuse me. Cache is constructed as an 8-entry SRAM. Each entry, okay, 8 entry. Each entry or set contains one line consisting of 32 bit of data. Okay. Wait. Acha, okay. Right, correct. So Each entry or set contains one line consisting of 32 bits of data, 27 bits of tag, one valid bit. I'm sorry. So tag के लिए 27 bits, one valid bit. And one valid bit. The cache is accessed using 32-bit address. The two least significant bits, the byte offset bits, are ignored for word accesses. Okay. So okay, tag is 27, set is 3 bits, set is 0. Okay. Yeah, after seeing this I got the idea. Okay. The byte offset bits are ignored for word accesses. Next 3 bits, the set bits, specify the entry or set in the cache. Okay. A load instruction reads the specified entry from the cache and checks the tag and valid bits. So next 3 bits, specify the entry or set in the cache. A load instruction reads specified entry from the cache. Okay, if there is an instruction called load from PC CPU, then that instruction has to be like that whatever the PC has to wants to load the data from a specific address, that address will be selected. That is divided into tag, set, and byte offset, and the data is placed here 32 bits, which is like we have already discussed that it is a what is that 2 power 32, right? So it is actually 2 power 30. 2 power 30 is 1 GB, right? 1 GB. So 1 gigs, 10 power 9, 10 power 9, and 10 power 9 locations. I have to fetch single location. Okay. Specified entry from the cache and checks the tag and valid bits. If the tag matches, okay, tag matches, the significant. Okay, it's like cache memory, which is SRAM. Besides storing the data, let's say 32 bits, it actually stores extra tag bits as well, isn't it? It stores tag bits. Okay, since it is a 8-line cache, so 3 bits can be also. Okay, this makes sense. Okay. This will select some column that makes sense. I would say banks, we'll see later. So tag will check whether it is okay. Let's say this is main memory. Hmm? For for our ease of understanding, I have divided each row. Like there will be some rows, right? You have some rows. Let's say, for simplicity, there are power 10 minus 1, that is 1023 lines. This is 0, 1. Hmm? So, and each line contains 32 bits. Hmm? So, this is clear, right? So, what I'm gonna be doing is I have a cache which is 8-bit wide. Hmm? And huh, I have got an idea, like intuition, that let's say this memory got extended. Okay. Hmm? So 4 blocks. So this will become 100 110 110 111, right? And I maintained this uh, 2 part 10 lines as well, like, huh, but this has increased. So in a way I have added an extra address line. So uh, instead of having 12 address lines, I have added one more address line to power 13. Because see, the in 2 part 12 I can access how many bytes? I can access 4 kilobytes. In 2 part 13 I can access 8 kilobytes. So double over here. So this is the, you can see the illustration. So now um, that's the thing. I can make this as offset. I mean, I can fix this. 100 is fixed. I can access this. Okay. So it's difficult to explain until I get a good picture of entire thing. So byte offset is fixed. Set is for selecting like set number. Tag is the remaining address line. So what they have done is oh my god. Very bad. So I have tag, I have set, and these are offset heads. So let's say 0. Okay? And I have cache memory. Okay, so this is set 0, set 1, set 7. This can be used to select the set. And that is done, right? So actually this single set contains a tag and data. This will be given to output. Tag is given to a comparator. It's a hit if it is a match, and this is valid bit, right? So if valid bit is 1, then only we can say that it is a hit. Okay, valid bit is okay. Yeah, I'm wrong actually. This is tag. Okay, so now it is a hit. Maybe it's better to go for white now. So this is 32 bits. Tag is if 3 bits for this, 2 bits for 5 bits. Con 10, 27. Total total 32, right? So yeah. In programming flowchart wala, this is not a decision block. This is the decision block. So choose the type. Intent is run. Each entry or set contains one line consisting of 32 bits. Tag one valid bit. The cache is accessed using 32-bit address. The two least byte offset bits are ignored for word accesses. The next three bits okay. So actually, hmm, the cache is accessed using 32-bit address. Newer for word accesses. The next three bits, the set bits, specify the entry or set in the cache. A load instruction is the specific entry in the cache and checks the tag and valid bits. If the tag matches the more significant 27 bits of address and the valid bit is 1, the cache hits and the data is returned to the processor. Otherwise, the cache misses and the memory system must fetch the data from main memory. Temporal locality and direct with a direct mapped cache. Okay. Loops are a common source. Few seconds, please. Loops are a common source of temporal and spatial locality in applications. Using the 8 entry cache 8.7. 8 entry cache, now I got that what is 8 entry cache, because uh, you can say that at a time, like in a given point of time, single cycle of SRAM write operation, I can take multiple inputs. Let's say there are 4 columns in SRAM. Each column can accommodate 32 bits. So in a way, each row has 128 bits. Let's say 32 bits as a one word for this SRAM. So 4 words can be simultaneously fetched from one memory to the other. Like it's a main memory to SRAM cache memory. So that is entry 1 achieves. So this is here we have 8 entry. I specified 4 entry. Using the 8 entry cache 8.7. 8.7 is this region. Okay. 8 entry, or is it talking about set? Maybe it's talking like it's written about set count, number of sets. Show the contents of cache after executing the following silly loop units assembly code. Assume that the cache is initially empty. What is the mystery? Add immediate 0th location 5. No, immediate data 0 plus 5. T0 will be having 5. Branch equal. So we will be checking whether it is equal or not. No, it's not equal. If it is equal, go to 10. LW is load word or what. Then in that sense, I will do that T1 will get $4 euro. Okay. $3 T3 0 add immediate T0 -1. I'm talking about cache, right? Forgot. So jump to so actually this runs for let's come for it is 5 4 3 2 1. It runs for 5 times. So we are loading things. So what he is saying is loops are common source of temperance measure locality. Using the 8-entry cache of function, show the contents of the cache after executing. Ensure that the cache is initially empty and reset. Dude. 4 C. Don't know. Usually the program contains a loop that repeats for 5 iterations. That I know. Each iteration involves 3 memory accesses. Yes, load word, load word, load word. Okay, that also makes sense. And resulting in 15 total memory accesses. First time loop executes. The cache is empty and the data must be fetched from main memory locations 04 which is 100. ABC is 10 11 12 1100 1000 into cache sets 132. Okay. So, 100 okay. 1 3 2. However, the next 4 times the loop executes, the data is found in the cache. The red one shows the contents of the cache during the hash refers to memory address. However, next 4 times loop executed data is found in the cache. The red panel shows the contents of the cache during the hash. The tags are all 0 because the 27 bits of the address are 0. Okay, got it. The miss rate is 315. The tags allows when two recently accessed addresses map to same cache, when two recently addressed accessed addresses to same cache block. Yeah, this is what I'm talking about, right? So yeah, this one. So we are in a way accessing this one. And what if I have this one? What if I want to access this one? So I'm getting misses. Like these rows are filled with these data, main memory row data, row bytes. So obviously there will be misses. Yeah. Good thing that I got that out. Now I'm getting some feeling. It's not boring. When two recently accessed addresses maps to same cache block. Okay. A conflict occurs. And the most recently accessed address evicts the previous one from the block. Evicts. Direct map cache have only one block in each set. So two addresses that map to same set always cause a conflict. Correct. Two addresses that map to same set. Direct map cache has one block in each set. Two addresses that map to the same set always cause a fight. Example on the next page illustrates conflicts. Okay. During the initial execution of the data metadata code is loaded into segment. When data is loaded into segment, editing the data from address or upon editing the data from address or Upon the second execution of the loop, the pattern repeats and the cache must refresh data at either for emptying data from address 24. The two addresses conflict and miss rate is 100%. Hmm. Makes sense. Then I'm getting that doubt now. Violate that one. Mm, okay, this 04024 address, whatever the address that it, whatever the address it has, 04 is the address itself, right? So it is 0100, and 24 is like again first four bits are 0100. There is a conflict, so both the set address is same for load word t1. T1 is loaded with 0, T2 is loaded with 0. So both the instructions are having the same set address. So when the load word instruction T1 is loaded into the cache, and when we try to load this instruction of T2, T1 will get replaced. So again, it goes on again and again. So let's say initially we will have nothing. Then we must need to take from the main memory. Okay, first item we took from the main memory. It is a mess. T1 we have got T1, and now we need T2 load one. Set address is same, and I have to go for the main memory. It's a mess, right? So this loop goes on forever. How many times you repeat the program, it will be a mess, 100% mess. So this is a conflict, cache block conflict. Okay. So mm, wait, why this is a mess? I forgot. Like I forgot. The first time the loop executes cache is empty, but okay. So there will be three messes. Okay, that is understandable. Three misread. Mm, yeah, that's why I asked. Okay. Let me take the snap screen. Paste it here. Oh my god. cycle cache empty. So when you access 04, it's a mess, and when you access 08, it's a mess, and when you access C, it's a mess. But second cycle loop cache isn't empty. So when you access 04, we already have that data, so it's a hit. When you access 8, it's again a hit. When you access C, again a hit. Wait, I forgot my bottle outside. No minutes. So now in third cycle, again there will be hit, and fourth and fifth cycle as well. So in total, if there are 3 misses, and how many attempts, how many accesses? 15. So it will be 20% of misrep. Again, you'll get to know the same set is being accessed. First cycle cache empty. So 004 is a mess. 024 is a mess. Then second cycle. Is a mess again. Why? Because these two share same set. 024 is a mess. So cross off. Apply injections here, same set address. That's how. Okay, how do we wait a second. So my intuition is actually wrong here. Let me show you. This is actually 32 bit. As of I think it's 32. Mm, 32 or 8. Let me come to that again. So there is a conflict, right? There are multiple misses. Set test set wala conflict. So how do we how do we resolve this? So multi-way set associative cache. So an n-way set associative cache reduces conflicts by providing n blocks. In each set where data mapping to a set might be found, an n-way set associative cache reduces conflicts by providing n blocks in each set where data mapping to that set okay might be found. Each memory address still maps to a specific set, but it can map to any one of the n blocks in the set. Hence, a direct map cache is another name for a one-way set associative cache. Acha, okay. And is also called degree of associativity. Shows the hardware for us. 8 word can do it. The cache now has only s equal to 4 sets rather than 8. 0 like 000 and 100 is in the same set. 001 and 101 is in the same. Yeah. So zero. Okay. Okay. Depending on this signal, if it had been a hit for hit 1, then we have to take this data. If it is 0, then goes for that one. And okay, 0 into and we finally take. There's only 2 segments rather than 3 are used to select this. The tag increases from 27 to 28. Each set contains 2 ways or decrease of associated. Each way consists of data block, yep, only valid and tag bits. The cache reads blocks in both ways. The selected set and checks the tags and valid bits. If a hit occurs in a form of multiplexer, its data from that set associated caches generally lower bit rates than direct map associated parity because they have fewer conflicts. However, set associated caches are usually slower and somewhat more expensive to because the output multiplexer and additional comparison. They also raise the question of which way to replace when the ways are full. This is addressed further in 8.3.3. Most commercial systems use set associated caches. If I run this program in the set associative cache mode, I accessed 4 8 serial which are of which belong to different sets. Then that's fine. 100, so that is fine. But when it comes to this one now, this is 0100 and again 0100. So same set is accessed. So instead of let's say in way 0 we have placed 0 for location data, and in way 1 we can place 0 to 4 data. because it's yeah, replacement. Least recently used. Least recently used LR. Correct. Here, this is the least recently used one. This is the latest one. So this will be something. Now it's making sense. But my question still remain there in my back of my head that yeah, why would we choose like this? So this is 32 bit. Mostly, yeah, correct, 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 correct. Yeah, correct, 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 correct. So I need to change here. Okay. So this is actually wrong. Actually, entire word of email memory is 32. So disclaimer that do not use this. So initially we go for what we say. We should not mention that direct, like one way associated cache memory, set associated cache memory, but we have to mention direct map cache memory. So direct map cache memory we have like it has a direct relation with the main memory. Okay, since we have 4 bytes, 4 columns. Okay, somehow I just scrambled this to 32 locations into 2 power 30 by 2 square locations. So I have these 4 columns and 2 power 30 2 power 30 rows. So in cache, I'll store 32 bits. Okay, but the last 2 bits won't be changing. Those will be like while accessing while I'm accessing this row, I would just simply mention initial digits as 0. Then later on, according to the row, I will just specify the 30 bits. Thus, I will be accessing the row 0. I just pull out these entire 32 bits using burst mode or something else, somehow I'll reduce my time. Anyway, this row is selected, right? And then I'll go to the next row and bring out all the 32 bits into this. Thus, since this is an 8-line cache or a 4-line cache, it's a 4-line cache. 4 blocks are there. Each block is 32 bits. Okay. So after filling out 4 lines, 4 blocks, I need to again come back to this. Why? Because after going from rows like 0000, 0001, 0010, 0000, the fourth row, like I mean, 0th one, 2, 3, 4th row will be 0, 1, 0, 0. So the least 2 bits are 0. So I'll again come back to this now. I'll again come back to this. 0, 0. This is 0, 1, 1, 0, 1, 1. Again 0, 0, 0, 1, 1, 0, 1. Again it repeats itself. Let's say there is a 8-line cache. I'll go for 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 2, 0, then 1, 0, 0. Again here, so 3 bits. Set bits are 3. Offset bits are actually 2. Okay. And I'll be ending up with 27 tag bits. Okay. So there are some conflicts in here. We know what are those conflicts. One is temporal locality. I have used this and I'll come again in some time. So there is some conflict. Initially, like when we start the PC, then there will be no data. So definitely it is a miss. And here, same set cache memory, same cache block is used by 2 instructions again and again subsequently. So they'll just replace each other. So every time it's a mess. So this is an issue. So why this is a temporal locality conflict? Because we are not replacing anything that is there in the edges and columns in a main memory. We are replacing what do we say? Might be adjacent rows or may not be. We are replacing rows in a main memory. Okay. And those rows are mapped to single set in cache memory. So when you use a program where the instructions, let's say some X instruction is pointing to set 0 and Y instruction, the subsequent one, is pointing to the same set in cache, then while running a program, when the X instruction is executed, it is replacing, like let's say when in the start X instruction will be loaded, it's a miss obviously. Y instruction is executed to the same set. It has to come to the same set, same location, and it is a one-way entry. So it has to be replaced. That X location instruction has to be replaced by Y instruction. It's a miss. We replace. Again, it's a past track, right? So again, when we come here, in the past I have replaced X with Y. Now Y is there. I need to again replace the Y with X. So this is a temporal conflict. This takes time, but it's a good stuff. Set associative cache miss rate. Repeat example 8.7 using 8 for two-way set associative cache from 8.9. Figure 8.9. Okay. 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 So he is asking us to implement this. He's asking us to implement this. Listen. Two-way set associativity. Using 8-word. So 8-word in the sense each cache block contains 8 words, and since it is a two-way, one way will have 4 words, that is 32 bits, and other way will have 4 words, that is 32 bits. So let's say this is way 1, this is way 0, let's say. So actually LW $T1 will be here, store 0, and LW $T2 0 is stored, and tag bits will be 24. Bits will be 24, and double 0 and 0 and 2 0 1 0 2 4, and that one will be 1 double 0 0 0 0 0. So these are offset bits. Those are offset bits. Since it is a byte addresser, so these are offset bits. And we have 0 and 0. So it is pointing to set 1, isn't it? So it is pointing to set 1. We have set 0 as well, which is empty, I would say. Or may not be. It's empty. So these will go to multiplexer, and definitely we will have a hit. So initially there will be 2 misses, and later on for further 4 loops there will be 8 hits, and in total there are 10 accesses, so it's like 20% mistake. Put memory accesses to address 424 map to set 1. However, the cache has 2 layers, so it can accommodate data from both addresses. During the first loop iteration of the cache measures both addresses. Fully associated cache. Okay. Oh my god, we have finally reached fully associated. Slowly we are reaching. Let's keep this pace. We should be able to finish this. A fully associative cache contains a single set with 8 ways. I need some rest. Give me 10 minutes.
close till I get up. Time is barely on our side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And to protect your soul.
So let me redraw this. This is layer 1, this is layer 0, and this is set 1 double 0 can come here and triple 0 also can come here. So I can never say that this is set 0. It contains 1 double 0. So this is set 1, 0 0 1, 1 0 1. This is set 2, 0 1 0, 1 1 0. This is set 3, 0 double 1, 1 double 1. So here I would be having a valid bit and a valid bit here as well. And there is a tag here as well. So these tags are given to address. Address is here. Address is here. This is tag. This is data. Actually, why would address contain data? This is set. This is offset by bits. Sorry, offset bytes. Yeah, bytes. You can say bits. How many number? So something like that. So this tag is given to this one. We'll check whether it is equal or not, and say this will be given to this one, whether it is equal or not. So we'll just combine these two. Any one of these could result in a hit. This is hit 1 because it is a wait, we name it as hit 0 because it is coming from lazy. This is hit 1. So hello, 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 hello. So this is hit 1. Hello, hello, hello. So I'll be getting two datas, one from here, one from here, multiplex them, and the selection line would be let's place this on the left side. It will be clear according to the design. So I'll get the data. This is actually data. These are tags and these are red bits. That's how a set associative, two-way set associative data is being read out. And easy, let's fully associative. Okay, fully associative cache contains a single set with B ways. Yeah, makes sense. It can go anywhere. Where B is like fully associative, then it's really expensive, right? Two-way set associative itself requires mux 2 and some comparators, two comparators and an OR gate. If let's say three-way, let's say cache lines are 8 and I make it fully associative, then I need mux 8 comparators and 8 input OR gate. Fully associative cache contains a single set with B ways, where B is number of blocks. A memory address can map to a block is cache contains a single set with B ways, where there is the full number of blocks, where B is the number of blocks. Memory address can map to a block in any of these ways. Correct. A fully associative cache is another name for a B-way set associative cache. Then in that sense, I do not have any set bits, right? Except those offset byte bits. I do not have any set bits. So yeah, except those two, I'll be left with 30 tag bits with one valid bit. A fully associative cache shows the SRAM area fully associative cache with 8 blocks upon a data request. 8 comparisons must be made because the data in E block similarly is proper data fully associative caches. To have fewest conflict messages for given cache capacity, but they require additional tech computation. They are best suited to replacement block size. For now, we are using something like that. Could be wrong, could be right. We don't know. Block size. Let me go back to that initial doubt that we have, at least I have. Mm, so number of blocks and sets are equal. Okay, that's a particular in an n-way set associative capacity set contains n blocks. Okay, the address still maps to Init set equals to by n. Correct. Let's say blocks are 8. Yeah, these are 2 sets. But the data from the address can blocks. The mentioned 8 is my mic on? Okay. The mentioned 8 word capacity, not 8 bit. I got sorry. I interpreted that as 8 bit. So this one, this is not 8-bit. This is actually cache memory has 8 word, okay, 8 word capacity. That in the sense, like it can accommodate 8 words. Each word is 32-bit. We begin with one word block size, then generalize later to larger. Shit, man. Fine. We have associativity, we have sets, set address. So we got to know how to, like, how is data found using these techniques. If it is a direct map, we can directly check the AC. You need AC.
Light, no. The light.
हाँ लाइट हाँ सबसे लाइट ही था
सो जाता इसलिए बढ़िया लाइव आ जाओ
बीच बीच में 10 मिनट सोया था
हाँ मैं देखा तो एक्चुअली ना आई गॉट वन पेपर मैं तो आ जाऊंगा किसी रात को आ जाऊंगा बैठ जाऊंगा 10 बजे के लिए ये ऑप्टिमा खत्म होगा
But currently cadence is not working.
स्टिल नॉट वर्किंग
I didn't check today.
ओके मेरे पास आईडी है मैं उसको पहले लाइक करूंगा फिर मैं डिजाइन करता हूँ किसमें गया 61 मैंने बोला
180.
180 में गया प्लीज उसी में लगा 180
सोहम सर का यूज कर.
नहीं मेरे पास है राघवेंद्र का है
Okay.
उसी यूज करूंगा
कुछ एरर्स आ रहे हैं.
एरर्स आ रहे हैं मैं देखता हूँ मैं पहले ये खत्म कर लूँ मुझे एक बार बिजनेस से लगेगी उसके बाद मेरा टाइम मिलेगा उसके बाद रगड़ दूंगा होगा तो मैं भी यही सोच आई विल आल्सो सी इट नो प्रॉब्लम
कोई नहीं आ रहा है.
डिपेंड्स करता है ना डिपेंड हाँ मतलब कोई आएगा नहीं होगा शिवा के तुम बढ़ जाएंगे काम कर लूँगा
हाँ.
2 3 दिन पकड़ के ऐसे काम खत्म करके और एक दिन सो जाऊँगा फिर दिन उठ फिर शुरू करेंगे बाकी
बाकी मतलब रिसर्च और ये रिसर्च.
हाँ रिसर्च तो करना ही है वो तो छोड़ना ही नहीं आई कैन नॉट लाइक लीव रिसर्च still like side by side I have to do my thing I have to complete my degree thing as well as
इंटर्नशिप क्रैक कर.
internship crack करने के लिए मुझे तैयारी करके रखनी होगी ना not internship placement का if I able to crack a placement that's also good placement अगर मेरा हो जाएगा तो मेरे पास because nobody guided me
Like first of all, no one is there interested in this.
no they are all doing stuff analog stuff analog and all I have no interest of doing it. Like digital में मुझे आ रहा है interest like system में लग पड़ा तो I got fascinated 8 दिन में खा गया मुझे सिंटैक्स मुझे पता था ना सिंटैक्स मुझे आता है मैं बोला था ना मैंने वेरिलॉग पढ़ा उसके बाद वेरिलॉग मैंने एक कोर्स किया एनपीटीईएल से उसके बाद सिस्टम वेरिलॉग का ये कोर्स किया अभी प्रोजेक्ट 4 किया थोड़ा जो प्रोजेक्ट है ना अम्बा वाला उससे पहले दो तीन एफईओ और एक
SPI UART.
हाँ यूएआरटी और एसपीआईसी वो कर लूँगा बेसिक चार उसको होल्ड कर लूँगा अम्बा प्रोटोकॉल भी जब आना तब स्विच कर लूँगा पहले थोड़ा प्रैक्टिस करना पड़ेगा सिस्टम वेरिलॉग मतलब ऐसा नहीं कि मैं साथ में ना आए तो वो नहीं I don't know still I don't know anything crux I got like what is happening in the code
Skeleton you got to know.
skeleton I got that planning how verification plan was how the architecture how the environment is there how the generator is sending protocol those protocol have to develop generator and then one with scoreboard and between monitor and interfaces are important for like converting signals no converting signals and putting the DUV output nice thing this is
Like this is standard thing. It doesn't change.
these are standard industrial standard
There is no creative work.
You
You just
no
upgrade protocols.
protocol yeah
You
Now,
did one protocol.
these are like
then
block level
total.
things you will get to know what are block level you should know block level
So that's why they emphasize ki you should know multiple protocols.
that is why that is why I want to learn like RISC-V also RISC-V is good thing RISC-V सीख जाऊंगा तो बहुत कुछ like open हो जाएगा ना और I will get to know like these things जो मैं पढ़ रहा हूँ
Even why like cache memory का भी पता चलेगा. Like
SRAM
how instructions are fetched.
हाँ
Why it is seeking some instructions from memory. How the data is coming. How the delay affects this entire process execution.
if you are available in next semester na I'm going to audit one course advanced computer architecture
Okay.
that is why I'm learning computer architecture
इधर का
सुरेश पुरेनी
easy taking.
हाँ मैं बैठ जाऊंगा जाके just I will go and sit
Okay.
you can come with me
I asked आशीष है ना
हाँ
आशीष भैया
हाँ that's
CSG वाला
CSG हाँ
उनको पूछा था and he said he is not taking computer architecture course.
he's not taking
सुरेश पुरनी से.
depends अभी list आएगी पता चलेगी because that course started previous year
Okay.
advanced computer architecture okay
Then it's really crucial to know RISC-V basic one.
basic. No, no, he will go with risk.
Although he starts, but he'll just skim through the concepts. No?
I have slides.
Okay,
I have slides. I collected everything.
you have slides of the advanced computer.
Architecture, like all the syllabus.
उसमें बेसिक वाला उठा के पढ़ लेंगे.
स्लाइड्स है मेरे पास, मतलब जो सर ने पढ़ाया है ना, तो मेरे पास स्लाइड्स रखे हुए हैं. मैंने मांग लिया ना विष्णु के पास था, विष्णु ने लिया था ना.
I think I have those.
विष्णु ने शेयर किया था मुझे.
इसमें पाइपलाइनिंग है.
पाइपलाइनिंग में
Bubbling, starting.
हाँ.
I think I have those.
हाँ, those are like advanced thing ना.
So he teaches pipelining.
He teaches only pipelining in this course.
Yeah, I guess so.
Still,
Pipelining and how the control unit manages everything.
okay, control unit and pipelining.
He doesn't tell about ALU all that.
ALU
Like ALU can be available.
ALU तो
It
ठीक
is
है.
available.
हाँ.
He tells about control.
Control unit is important. Control unit is very
Control
important.
is the main heart.
main thing.
Timing का issue.
टाइमिंग का इशू वही होता है ना. टाइमर चाहिए होता है उसको. वही कंट्रोल यूनिट.
Okay, विष्णु. वो जो ब्राउन वाइट कलर में होते हैं ना पीपीटी.
हाँ वही.
हाँ.
विष्णु तुमने लिया होगा. मैंने भी लिया. मैं उसको पढ़ा नहीं हूँ. मैं सोचा पहले पढ़ लेता हूँ, बेसिक पहले रिवाइज कर लेता हूँ. मैंने सब पढ़ा है, कैश शीट, कैश फिनिश, ये सब.
These are like
डायरेक्ट मैपिंग सेटअप.
सुनने में बढ़िया लगता है.
हाँ.
Like अजीब सा लगता है. It would take around few weeks. It's not like that. They're easy.
हाँ.
CPU एक instruction को ढूंढेगा. It will go to cache. If it is there, it is a hit. If it's not there, it is a miss. It will go to main memory.
हिट का भी फिर ये है ना, परसेंटेज हिट और कितना बार हिट.
In 100 accesses, let's say 50.
Hit means like वो tag मिल जाता है proper. You got a tag.
Yeah.
But the data is there is not, but that depends on the position. There is one address ना 1100, last two bits are the position of data in that tag. That is on direct mapping, set of between different
sets होते. If sets are 0, that is direct map.
Direct mapping. हाँ. Sets are 0 then direct. That is it. Cache is important. Virtual memory,
sets are 0. It is a full associative. There are no like you don't need to select any set. Everything is set.
It will not direct mapping. Direct mapping is set. Set मतलब भी direct mapping है.
Set है, but only one word है, like one block.
One block. वो block को consist करता है. वो मैं समझ रहा हूँ. I am telling you, we also virtual memory.
Virtual memory is hard disk thing.
Hard disk thing. Secondary memory.
इसमें पेजेस का कॉन्सेप्ट आता है ना.
पेजेस ना, हाँ वही.
पेजेस उठा के मेन मेमोरी में
डालो, फिर मेन मेमोरी से फिर वो कैश में आता है, फिर कैश पर फिर वो
इसमें भी है
प्रोसेसिंग होती है वही. तो वो पढ़ाया था उसने, सुरेश पुटिनी ने, बेसिक कोर्स में. ओके. बेसिक कंप्यूटर आर्किटेक्चर. ये
सब नहीं देखा था मैंने. He just sent me pipelining videos.
Okay,
pipelining PPT.
No, I have every PPT, each and every. He मतलब उन्हें पढ़ाया है, वर्चुअल पढ़ाया है, कैश मेमोरी पढ़ाया है, बहुत कुछ पढ़ाया है.
Send me those.
I will send you. Like मैं zip बना के भेजूँ, मेरे पास है, भेजा उसने. तो रिस्क 5 करते हैं, ठीक है. पहले रैम कर देता हूँ, डी रैम करके फिर रिस्क देखता हूँ, कोप अप करने की कोशिश करता हूँ. टाइम नहीं.
डी रैम देखने में बहुत लाइक फैसिनेटिंग लग रहा है. हाँ.
इजी होगा लेकिन एज कंपेयर टू
if you know the design. नहीं DRAM नहीं बोल रहा हूँ, verification related.
Okay, verification.
DDR4 verification.
DDR4 verification.
Address generation, data खुलना है, verify करना है.
हाँ, verify करो फिर वहाँ टाइम लगेगा. ये सारी चीजें ना Synopsys tools में करना चाहिए, लेकिन that tool is not working. That is
corrupted.
Maybe VCS is not working. I have some commands. There is one group I was there. When the VCS was installing it. I have those commands. We will try it sometime. Okay.
Although it's not really necessary, but
like
it gives an edge.
Tools, if you know tools now, it will be like good thing. Like I know to like work on Synopsys. Just spice things. Let's see what will happen. धीरे-धीरे move करेंगे. frequently नहीं कर सकते, not able to
I targeted that 30 pages cache memory.
today.
Like you have completed that cache memory seeing videos.
हाँ,
I'm trying to read those 30 pages.
I am not able. No, he told me these things. I still like.
Videos में like it's kind of guiding us. हमारा mind को
Look, I just want to know the crux of the
mm,
cache. Got it?
yeah,
Then I will go to deeply. What is happening?
मतलब you want to know how cache replacement policies
हाँ
take
हाँ,
place,
how everything works.
how writing is done.
हाँ. Like reading books is a good habit, but I'm not very fond of because I have less time. Na. If I start reading books, na, sir will ask where the books.
I'm reading books.
I'm reading books. Who told you to learn cache? No. Your project, your research work doesn't contain cache. What will you do? Okay.
Mm. As of now, we have been discussing only this block size as one word. One word in the sense, mm, a word is related to one word is related to main memory word. Okay, if let's say main memory has 32 bits in each row, and if I consider that as a continuous data, then 32 bits is termed as a word for main memory. So in cache memory, we have been discussing that each cache block contains 32 bits, which is main memory word. Okay. Now we are increasing block size. Okay. So now I'm getting, okay, I'm able to connect the dots now with Anuj's classes. Until now, we have like we either have hit or a miss. If it is a hit, then the time to access that data is t. If it is a miss, then we have to go for main memory and we have to fetch that data. That is t hit, like t miss. In that, instead of bringing one word, let's say main memory has multiple words in single row. So exploiting spatial locality property, I would bring entire row in one go, and that fetching like while fetching that entire row, I could utilize burst mode. If the hardware has main memory, hardware has let's say there are 16 modes, and I have mux 16, so I can have burst of 16 modes in 16 cycles. So I would be reducing that time to decode the row. Okay, okay. Mhm. Mhm. Block size. The previous examples were able to take advantage only for temporal locality. Yeah, so up till now we only cared about the temporal locality, those instructions. If there are some conflicts, we go for more than one way associativity. Let's say there are two set associative 8-line cache. Then I have four sets of cache blocks, each containing two cache blocks. So instead of that, I may use two-way. This is one way, right? Okay. I may use two-way, two set associative cache blocks, where there are two ways to enter the same set. It's not like it's not like what would we say? Mm, Way here represent the hardware nerve. Like if there are two ways, so that two ways might mean that it is a demux. So input will be data and demultiplexed outputs will be two ways. So based on the replacement policies, I can select the output line. Yeah, selection lines can come from replacement policies control related. If there is a one way, then there is no choice. I have to place that in Mm, mm, mm. Actually, I have a doubt. This is right. In direct mapping, अच्छा ओके ये तो सेट एसोसिएटेड ओके let's see. Mm, okay, got it. I just got confused with the representations. Okay. Mm, yeah, fine. Box size. I'll just copy paste this. So see. Okay, now box size. Let's go for size. Previous examples were able to take advantage only. Sorry. Temporal locality because the block size was one. Okay. Like, hmm, what would you say? uh, See, to run this program, if this instruction will be executed, like it seeks for the data in location field, it goes to cache. Initially, there is no data in cache. So at start, we have to, it's definitely a miss. We have to go for main memory. And this one, so while bringing the data from this address from main memory to the cache, these two actually point to the same set of locations, like same set. So they'll just replace each other. So this is a temporal thing. टाइम के साथ चेंज होता है, so it changes with time. So to avoid these conflicts, we kind of create multiple paths for same set. So in a way we are creating two copies, like two spaces, two locations for set 0, set 1, set 2, set 3. Earlier it would have been set 0 to set 7, total 8 cache blocks. Now those are only 4 sets with two-way, like two locations are there to store. Okay, so that is temporal kind of thing, temporal locality. Like let's say you in a program we are accessing 0th location, then in future we might use 100. 100 is not the thing. What could we say? We could say we could say 8, we could say 880, reasonable. 80 and 0th location will point to the same site. That's how we get temporal conflict. To avoid this, we may use multiple ways, multiple way associative, set associative, cache mapping. We are just mapping main memory to the cache. These are just techniques. So now cache memory is not just a single word, it has more than one word, that is block size. So I will first write that cache. Oh my god. Cache memory has more than one word. Here word is main memory. Main memory word simply. Okay. So a cache uses larger blocks to hold several consecutive blocks. The advantage of a block size greater than 1 is that when a miss occurs and the word is fetched into the cache, okay, yeah, the adjacent words in the block are also fetched. Therefore, subsequent accesses are more likely to hit because of spatial locality. However, a large block size means that a fixed size cache will have fewer blocks. Like let's say you have 8 by 8, 8 by 8 innocence. You have, let's say, 8 by 8 SRAM cache memory. 8 cache lines are there. How I make your let's say you have 8 by 8, 8 cache lines. 1, 2, 3, 4, 5, 6, 7, 8, and each is 8 bits. We can say 1 1. So this is SRAM cache. Now let's say you have 8 by 16. So that is these are only 8 lines. And here I have 2 words, word 0, word 1. That's it. So yeah, you have this fixed cache size. Let's say there is a fixed cache size. So however, a larger block size means that a fixed size cache will have fewer blocks. So let's say let's say I want to make this 8x16 as cache has more block size. Okay, I'm making this to have a more block size. So I have 4 lines. Word 0, word 1, word 2, word 3. So as you are trying to exploit the spatial property, spatial locality, in a way you are reducing the number of cache lines available. So have fewer blocks, like you have 4 blocks with a bigger size block size. Here you have 8 blocks with 2 words. Here you have 4 blocks with 4 words. That's the thing. So why should we care about this number of blocks? Because one block corresponds to one program, let's say, and other block corresponds to another program. In such a way I can accommodate, let's say, 4 programs, and if I want another 5th program to be placed in cache, then one of the program has to be replaced. And in a way we are not able to accommodate more programs than earlier cache configuration dimensions. So that is the thing. This may lead to more conflicts, increasing the mismatch. So it's a balancing thing, trade-off. What do you want? Like, you want block size to be more, then reduce the blocks. If you want more number of programs to be executed simultaneously, increase the block lines, number of blocks, just reduce the block size. Moreover, it takes more time to fetch the missing cache block after a miss. Because you have increased this block size, right? This is 4 words. This is actually 2 words, right? You have increased by +2. Let's say this takes around tmiss is tmiss, okay? How this time is calculated? It is the time that is taken to fetch 2 words from main memory in the same group. But here we need to fetch 4 words. Then approximately it would take 2 tmiss times, right? 2 tmiss cycles. This is tmiss cycles. One cycle time we don't know. some cycle time. So that is the thing. The fetch time increases. Time required to load the missing block into the cache is called miss penalty. Okay. So if uh, mm, data word, okay, if data word is missing, there is a miss, then time to fetch that missing word along with the subsequent words will take some time, that is tedious. This will eventually increase because of the block size which has increased, right? So this is called miss penalty. If there is a miss, you have to pay some penalty in fetching those words. Okay, let me just highlight this. Miss penalty. So time required array and required to load the missing block into the cache. If the adjacent, okay, let me write it here as well. Miss penalty time to fetch entire block your row of main memory. No, it shouldn't be entire block um, as a consequence of miss. Okay, data miss would be data miss. Safety miss. Okay. The adjacent words in the block are not accessed later. Wait, if the adjacent words in the block are not accessed later, the effort of fetching them is wasted, obviously. Nevertheless, most real programs benefit from larger block size. Usually, entire program will be stored adjacently, adjacent addresses. So spatial locality wouldn't go useless. It wouldn't go in vain. It will be helpful. So usually block size, larger block size will definitely help. Figure 8.12 shows the hardware for a C equal to 8 for direct mapped cache with a B equal to 4 word block size. Okay, the cache now has only B equal to C by B 2 blocks. Hardware for a C but map cache with the B4 word block size. Okay, like there are only 8 word directly mapped cache memory with a equal to 4 word block size. Okay, each block has 4 words and I'm getting 8 words directly mapped. So I would place these 8 words in 2 blocks, right? A direct mapped cache has 1 block in each set. That's true. So this cache is organized as two sets. Okay. Sorry, excuse me. So by it is anywhere we access this and okay, correct, correct, correct. Once again, what capacity? Okay, C stands for capacity. Capacity of cache memory, not capacitor. Okay, okay, got it. Gotcha. Gotcha, gotcha. I have gotcha. Gotcha. So that's I think are halfway through. We only two players to get this half time and mapped replacement techniques. Let me draw this. So I have tag, right? Tag, and I have some offset. I would say byte. Okay, brackets, I would say bits. And then I have excuse me. And I have 0, 0, that is byte addressable. Then I would go for forward request 2 bits. Okay. So for selecting the block, and then in each forward block, right? Block size is 4. That in the sense each cache block contains 4 nodes of 32 bits. So I need to select each one. So I need two bits. This is for word selection, word block, and there is a set selection. So we need to select the set. Since it is let me write down the spec. Spec is 8 word directly mapped. Direct map 8 word direct map cache with word block size. So I would need two sets, right? So for that I need a single bit. So let me write down this is valid, whether it is valid or not. This is tag and wait. Okay, this entire thing is tag. And then I have blocks. Okay. Hello, sir. Upendra is sitting in your place. So where were we? Okay, I have 8 capacity word, 8 word capacity of cache memory, direct map, word block size. Okay, so I would have tag, and let's take a different color. So it has 4 words. Since there are 4 word block size. Okay. Completely it is 8 words. Okay. So the remaining can be placed at the top. This is 4 word. This is the other 4 words. So for selecting a particular word, I would use word block. This is word block linking here to max. So there is 2 bits, 1 data, that is 32 bits. And for set, okay, set can be 1 or 0. So it is 1 bit only, 1 or 0. So tag when it comes to tag will be checked with both cache memory tag and address tag. We will generate a value hit if the valid bit is 1. So ungate it's a hit. Can you implement this in Cadence? Multiplexer, comparator, oh my god, comparator, multiplexer, which type? No. Memory address. What is this? There's only one bit as a multiplexer control offset bits. Okay. The most significant 27 transfers. Okay, only one tag is needed for hidden tag block. Yep, because the words in the block are consecutive addresses. Shows okay 1 and 3 cache fields for address and map into cache one. Okay. 8 where is 1 9C is okay 1 set 1 offset block offset is 3 and it maps to direct map cache. The byte offset guys give me some minutes. I'm doing live stream. I'm doing. Hmm? అదేంది అలా అంటారు ఎందుకు అసలు హ్మ్? అది వచ్చిందంటే వచ్చిందని కాదు ఎగ్జామ్ అయ్యిందంతే ఎగ్జామ్ అయ్యిందంతేగా మరి అదే ఎగ్జామ్ క్వాలిఫై అయ్యారు ఇంటర్వ్యూ అవ్వలేదుగా ఏమో మనకన్నా అవసరం So this is the first word and block offset. So this is the third word and like this emphasizes that for heights in the first word. Okay, like any word. And this emphasizes third word and zero first, second, third word and set one, not set zero. Outside between gets both in the block. In the block. And the next bit indicates the set remaining 27 bits are tagged for set 1 word 3 in the cache. The principle of using larger block sizes is okay. Spatial locality with a direct mapped cache. Repeat example 8.6 with 8 direct mapped cache with a field part by 8.6. 8.6. Okay. Screenshot. Would you come for dinner today? Hmm? Hmm? First check that JDM Punjabi Dhaba. Okay. Rehan sir suggested if you are planning to order food from outside, prefer this. It has some like good price ranges, good quality of food, quantity as well. Nanakramguda is here only, no? Wipro Circle. Oh, delivery itself is 50. He suggested aloo paratha. हाँ वही it's around 130 हाँ one paratha costs around 70 or 65 like if You order two, it's 130, for single 70. Sorry guys. So I have this 8 word 4 word block size, okay. So 04 04 is 100. So it would go for this is offset bits and this is for selecting a word, and this is for that set, right? So 04 would go to here, and then C is 1100. So actually it is set 0, this location. 8 will go to 1000. This is offset. This is offset 5. 2, then it will go to 8. So if I repeat this again, I have this as well, and this as well. So actually, if you run the loop for 5 times, there will be 3 instances, and like out of 15 accesses, it will be 20%, right? 1 by 20% misread. But previously it is how much? No, not 20%. Sorry. I forgot this. Like, if I to access 04 at the first place, I would be getting entire block, right? So out of 15 accesses, I would get only one miss. Then this is around 1 by 15. 1 by 15 is how much? 1 by 15. 100 by 15 is around 30, 96, 10, 6.66. 6.66. So this is the miss rate. Yeah. My god, guys, few minutes. Caches are organized as two-dimensional arrays. Rows are called sets. Columns are called arrays. Each entry in the array consists of a data block. Each entry in the array consists of data block and its associated value and tag bits. Caches are characterized by capacity, block size, number of blocks, that is B equals to CP, number of blocks in a set of that is set associativity. And if you split that into ways, um, that is number of ways, right? Okay, that is n. Yeah. number of ways and number of blocks in a set is the same thing. Set okay, direct mapped number of ways is one because there is no uh, there are no multiple blocks in a given set. There is only single block in a set. So there is no possibility of having multiple ways for a single set. Number of sets will be B is number of blocks. Set associativity is the least. So let's say number of ways is 1. Then number of blocks. Okay, set associativity n is 1, then it is just called as direct map. And if set associativity is B, then it is called fully associative. Beach में, like in middle of these two, you have set associativity. It's a 2. Then let's say blocks are number of blocks in a cache memory is 8, and your set associativity is 2. Then you have 4 sets. Summarize the various cache organizations. Each each addressing memory maps to only one set but can be stored in any of the ways. Cache capacity, associativity, set size, block size are typically powers of 2. This makes the cache fields, tags, set, block, offset bits, block, offset bits. Okay, I'm little confused. Block offset. Okay. Subsets of the address bits. Increasing the associativity n usually reduces the miss rate caused by conflicts. Okay, but higher associativity requires more tab comparators. Increasing the block size B takes advantage of spatial locality to reduce miss rate. However, it decreases the number of sets in the fixed size cache, therefore could lead to more conflicts. It also increases the miss penalty. Correct. And I'm getting headache, neck pain.
I lose myself. Spend a couple days with nobody else. Holding in my breath just to see if I can find you in my dreams. Oh, I'm getting tired. Why you're always trying so hard to make me surrender? Why you always in my face? Do you really think it's over? 'Cause I've been kicked when I'm so down, too much until it's numb, and there's nobody.
Everything is being recorded. Everything is getting recorded. How data is in a direct map cache, each address maps to a unique block. Okay. And set. If a set is full, then new data map loaded block in that set is replaced with new data. In set associate, like in direct mapping, there is no need for replacement text. It's really straightforward because each and every set is uh, belong to a specific location. So if a specific location is being selected, then it has to go to a specific set in the cache blocks. You cannot change anything. Our replacement policies techniques will come in handy in set associative and full associative caches. Okay. The cache must choose which block to evict. Evict in a sense, um, uh, pulling out the data. Okay. Evict when a cache set is full. The principle of temporal locality suggests, okay, temporal is timing. If past history says that some specific data is used, then it's likely to be used in near future as well. So that is temporal locality. Suggests that best choice is to evict the adjacent one as another bucket. You have thrown some data, let's say Z, time equals to 1 second. And you have thrown another data A at time equals to 3 seconds. So now I have Z here, A here, set 1. So basically, U is a flag bit, let's say, indication bit that which has been recently used. So recently used one is this one. So in a way, we utilize that U bit to change the circuitry in such a way that the next coming n data, n new data would enter this one, this bucket. So let's see how it is done. It's just a multiplexing thing, I guess. Let's say I have a multiplexer here, and there is a selection line that is new. Two lines are coming in, like actually it's a demux, right? Okay, it's a demux. One input comes, two outputs, two buckets. If the least least recently used is this one, let's say this is what this is what 0. So if this is the least recently used, then I'll make u as 0. Okay. Wait. So whoever is watching this, I think I have just confused you everyone. Least recently used is something that is I have said this now. So let's say Z is the least recently used among A and Z. A is the latest one. Okay. Now what I have said is Z has got has put in this bucket at t equal to 1 second and A at t equal to 3 seconds. So least recently used is this one, right? Okay. So I'll design a circuitry such that U becomes let's say this is U, this is 1. U becomes 0. And let's say some X is there, some Y is there. Y has been placed in this bucket at time t equal to 6 seconds. And x has been placed here at time equal to 8 seconds. 8 seconds में place किया था. So let's say x, but now I want to put a data c in z0. This is z0. So what should be replaced? So according to the temporal locality, least recently used is y. 6th second में डाला था उस bucket में. So I'll make u as 1. So if the least recently used is what I will make this. Okay. Let's see. Insert associative velocity. Wait. Best choice is to evict the least recently used because it is least likely to be used again. Hence, most associative caches have a least. Okay, most of the associated caches have least recently used replacement forms. In a two-way set associative cache, a bit like a use bit u indicates the way within a set as least recently used. Least recently used. Each time one of the ways is used, u is adjusted to indicate the other. Set associative caches with more than 2 ways. Tracking the least recently used way becomes complicated. To simplify the problem, the ways are often divided into 2 groups, and u indicates which ways was least recently used. Okay, it will be divided into 2 groups, and this u will indicate which group is least recently used. Upon replacement, a new block replaces a random block within the least recently used. Such a policy is called pseudo LRU. Like it's not completely LRU, it's not completely dependent on temporal locality that least recently used policy is utilized and that exact location has been evicted and new data has been placed. It's actually divided into groups and one of the group is selected. In that group, one of the block is evicted. One of the random block, yeah. And it's good enough in practice, okay. How do we generate this depends on the subtutor. Yeah, maybe if we have like set associative to 4, we may use u bits of size 2 bits. Then computer becomes complicated. Okay, what he said is this clear? Not it. I can't take it. We have valid and you have u bit. Okay, use bit or bit. So the same thing, man. You got to understand, right? The same thing. But now there is this thing called let me copy this. Should we draw this again and again? Now you have this is okay. I think I need to stop live streaming. Okay, it's been recording. Man, when did I start that? Shit. So in associativity 4, you don't have this, like you don't specifically select either of the 4. You would select, let me erase these as well. So you would select a single group. Okay, this is group 1, let's say group 0, group 1. So the data may go here or here, here or here. We don't know exactly. So this is 0, this is 1. This is 0, എല്ലാവർക്കും let's go for dinner. I'm getting that. So now advanced cache design is something that instead of having a single cache memory, we'll have some levels. So L1 cache, L2 cache, main memory, virtual memory. Modern systems use multiple levels of caches to decrease memory cost. This section explores the performance of a two-level caching system and examines how block size, associativity, cache capacity affect miss rate. This section also describes how caches handle stores or writes by using a write-through, write-back policy. Nice. Write-through, I can guess from CPU you would be writing through all the caches, or from main memory you would be writing to the CPU through all the caches, and write back, write through, write back. Okay, anything is so system with an do cache, multiple level caches, reducing miss rate, write policy. Okay, we finally entered writing wala cheez. I think it's enough for here. For me, at least for me, it's enough. And I need to know virtual memory and yeah, I need to know all these things. Address translation. Maybe I can study this later. But since I'm in a flow, it's better to study these paging result of let's complete that multiple level cache. So multiple level caches. Large caches are very rare because they are more likely to have cache and therefore have lower risk. However, large caches tend to be slower than small. Modern systems often use two levels of caches, as shown on the page. First level is small enough, provide one or two cycle access time. So the second level is good from SRAM but is larger and therefore slower than L1. Processor first looks for the data in L1. If the L1 misses, processor looks in the L2. If the L2 cache misses, the processor fetches the data from main memory. Some modern systems and even more levels of cache to the memory hierarchy. Some modern systems add even more levels of cache to the memory hierarchy because accessing main memory is so slow. System with L2 cache. Use the system of figure 8.16 access time of 1 10 100 cycles for the L1 L2 cache and main memory 8.16. Okay. Assume that L1 L2 caches have miss rates of 5% 20%. Specifically 5% of accesses that miss the L1 cache. Okay. 20% of those also miss the L2 cache. Okay, whatever. Okay, what is the average memory access time? So, saying that should I write? Okay, we have access times as 1 10 100. This is for L1 L2 and main memory. And he has mentioned that for L1 there is a miss rate of miss rates of 5%. Okay, and L2 has 20% respectively. Specifically, the 5% of accesses of the 5% of the accesses that miss L1. So L1 में जो भी कुछ like whatever the how many be the L1 caches be miss wala, out of that 5% will definitely missing L2, 20% of L2. Okay, let's forget this condition first. We'll just implement and find out the average memory access time using this. Later on, we'll go for the AMAT will be, if it is a hit, I'll get 1 cycle, and if it is a miss, I would be, if it is a miss, I would be going to L2. So L2 may, if it is a hit, it will be 10 cycles, and if it is a miss, it depends. It goes to main memory. Main memory takes around 100 seconds, and that is the end. It has to be there. So 100. But here we need to multiply the probability that L1 has this misrate, something like that. So it has a misrate of 5%. So hit rate of 95%. So I would say 95. Yeah, 95 by 100 is the hit rate. And this one is if it is a miss. And in that, if you are able to find out मिस रेट कितना है L1 का 5%. This will be multiplied by 5 by 100. Miss rate of L1. Miss rate of L1. And into, if there is a hit, it will take 10 seconds, and hit rate is 80%. 80 by 100. And if it is a miss rate is around 20%. So 20 by 100, and it will take 100 cycles. Okay, this is 0.95 plus 0.05. 80 by 100 is perfect. Perfect is 0.8. Okay, 0.88. 1/5. 1/5 is 20 into 100. Okay, 28. 28 into 5 over 100. 40. 140. 1.4. 1.4. 0.95. 2.35. But there is another condition. Yes, it is simple actually. Which one? This one. Now we'll see this one. So within this condition, specifically, after 5% of accesses of like 5%, specifically of the 5% of the accesses that miss L1 cache. Okay, those accesses that miss L1 cache, as it is 5%, 500, 20% of those. So let's say there are 100 accesses and 5 accesses are misses L1. So within that 5 accesses, one access, 20% of those also miss L2. So one of them will for sure miss L2. Okay, that is what he said. Somehow we got 2.4. Let's see. L1 is 5%, L2 is 20%, 5% of L1 miss, right? L1 is okay. 5% off. That means L1 cash. Okay. This rate of L1. 5% off. Accesses that may sell in cash. Okay. 20% of those also miss into cash. So it's kind of saying 20% of those will definitely miss into cash. Right? This rate of entry is 20. That's okay. So that's a separate thing. So I shouldn't include that. Mhm. Let's say there are 100 accesses. So it would likely that 5 accesses will fail with this, and in L2 it's most likely that 20 accesses will fail, and moreover